Krispy Kreme donuts, Chipotle and Nerds are built around a secret process people never see. They are products millions consume every day, but how they're produced always stayed under the radar until now. Today, we'll be diving into the factory process of these products, showcasing the truly fascinating methods that are used to produce the most famous brands in the world. For Krispy Kreme donuts, sifted flour drops into the mixer as a clean, loose stream. Sugar follows through a separate feeder. Yeast, salt, milk solids, and minor dry ingredients enter in smaller measured amounts. Water is added through a temperature-controlled line. Fat, egg ingredients, and flavor components flow in through closed pipes. The batch begins moving immediately, before the ingredients have time to settle into separate layers. The mixer arms pull dry flour into the liquid and push the mass across the bowl. At first, the mixture looks rough and broken. Dry patches cling to damp clumps. Then the dough tightens. It folds over itself and becomes elastic. The surface changes from powdery to smooth, with a slight shine from the fat and moisture. The dough must develop enough strength to trap gas during proofing, but not enough to become chewy. The mixer controls this with time, speed, and final dough temperature. When the dough reaches the right stretch, it leaves the bowl as a soft, warm mass. The dough moves into a divider. The divider cuts it into controlled portions for the sheeting line. Each portion rests briefly. During this rest, tension relaxes inside the dough, allowing it to roll flat without snapping back. The rested dough enters the first roller set. The rollers compress it into a thick slab. The slab moves into additional rollers, each set narrowing the gap slightly. The dough becomes a wide, even sheet. Its thickness is controlled because every later stage depends on this measurement. A light dusting of flour keeps the dough from sticking to the belts and rollers. Scrapers keep the roller surfaces clean. Side guides hold the sheet straight as it travels forward. The dough is now smooth, pale, and continuous. The sheet reaches the cutting drum. Circular blades press down in repeating rows. The outer blade cuts the main ring. A smaller inner blade removes the center. The cutter lifts, rotates, and presses again, making rows of raw donuts at high speed. The raw rings separate from the surrounding web of dough. The leftover dough lifts away on a return belt. It can be blended back into later dough in controlled amounts. The small center pieces move onto a separate path or are removed from the main ring line. The cut rings are flat and fragile. They move into the proofer on open trays or belts. Warm, humid air surrounds them. Yeast activity increases inside the dough. Carbon dioxide forms and fills the internal gluten network. The rings rise gradually. Their edges round out. The center holes widen slightly. The surface stays soft because humidity prevents drying. If the surface formed a dry skin, it would tear during expansion and crack in the fryer. The proofer controls temperature, humidity, and travel time. Each ring must become light enough to float, but strong enough to hold its shape. Underproofed dough stays dense. Overproofed dough becomes weak and can collapse. The correct proof creates a tall, airy structure. At the end of proofing, the rings transfer into hot oil. The movement must be gentle because the dough is full of gas. A rough transfer would flatten the cells and distort the ring. The proofed donuts touch the oil and begin floating. Steam pushes outward from the dough. The lower surface sets first. Tiny bubbles race along the edge and through the center opening. The ring expands slightly as heat reaches the interior. The first side turns golden. A mechanical turner flips each donut at the right point. The second side enters the oil and browns to match. The fryer carries the donuts forward in lanes so timing stays consistent. Oil temperature is held tightly. If it is too low, the donut absorbs too much oil and becomes heavy. If it is too high, the crust darkens before the center cooks. Filters remove loose crumbs from the oil so burnt particles do not stick to later donuts. The donuts leave the fryer on a draining conveyor. Excess oil falls through the mesh belt. The rings are fully cooked, but still hot and delicate. The crust is firm enough for transfer. The inside remains soft, open, and springy. The warm donuts move towards the glaze station. The glaze is prepared in a heated tank. Sugar, water, and flavoring components blend into a smooth liquid. Agitators keep the glaze uniform. Temperature controls how quickly it flows and how thinly it coats. The glaze circulates continuously. A pump lifts it from the tank to an overhead trough. From there, it falls as a curtain across the conveyor. The curtain must be even from side to side, so every donut receives the same coating. The donuts pass under the falling glaze. The liquid coats the top, rolls down the sides, and covers the inner ring. Excess glaze drains through the open belt and returns to the tank. The warm donut surface helps the glaze spread before it starts setting. As the donuts move forward, air passes over the surface. Moisture leaves the glaze. The coating changes from wet and fluid to smooth and lightly set. The donut remains soft inside, while the outside develops a thin sugar shell. Other Krispy Kreme donut formats branch from this same dough system. For filled donuts, the cutter makes solid rounds instead of rings. The rounds proof in the same warm, humid environment. They fry as closed pillows rather than open rings. The fryer turns them carefully, so both sides brown evenly. After frying, filled donuts cool before injection. Filling that enters a donut too hot can become unstable or leak. Once the donut reaches the right temperature, it moves into an injection station. Thin nozzles enter from the side. A pump delivers a measured amount of cream, custard, jelly, or flavored filling into the center. The filling spreads through the soft interior and expands the donut slightly. The nozzle withdraws, leaving a small entry point. The filled donut may then receive glaze, powdered sugar, icing, or decorative stripes. For chocolate iced donuts, the fried rings cool more than glazed rings. A cooler surface helps the icing sit on top instead of melting too thin. The donut passes under a coating head or touches a shallow icing surface. Chocolate icing spreads across the top and forms a smooth cap. Sprinkles are added while the icing is still tacky. A dispenser drops colored pieces across the moving donuts. The toppings strike the wet surface and stick. Loose pieces fall through the conveyor and are separated from the finished product stream. For powdered donuts, the product moves through a dusting chamber. Fine sugar falls from above, while the donut turns or passes through the powder zone. Excess sugar drops through screens and can be collected away from the product path. For striped donuts, narrow nozzles apply thin lines of icing across the top. The nozzles release a controlled flow while the donut moves below. The lines set as the donut continues through the cooling area. Finished donuts move into inspection. Cameras check shape, color, glaze coverage, icing placement, missing toppings, broken edges, distorted rings, and surface defects. Weight systems can detect missing filling or incorrect size. Rejected donuts leave the line automatically. Accepted donuts are spaced by timing belts. The belts create gaps so glaze and icing do not smear. Guide rails align each piece for packing. For boxed donuts, paperboard blanks open into trays or boxes. Donuts are placed in rows or grids. Ring donuts can sit close together once glaze has set. Iced and decorated donuts need more careful placement so toppings do not rub against another surface. The lid folds over the arrangement and protects the top. For clamshell packs, formed containers arrive open. Donuts are placed inside the base. The lid closes over the top and locks into place. The container holds the shape and prevents direct pressure on the surface. For wrapped single donuts, the product enters a flow wrapper. Printed film unwinds from a roll and folds around the donut. A lengthwise seal, closes the film tube. Cross-seal jaws close the front and back ends, then cut the package free. The film protects the donut and keeps the coating from contacting outside surfaces. Chipotle production begins with whole avocados being cut, mashed, and converted into guacamole before the other cold ingredients move into the assembly line. The avocados arrive firm enough to hold shape but soft enough to mash. They are rinsed, split, and separated from the pits. The green flesh is scooped from the skins and dropped into a mixing vessel. The texture at this stage is uneven, with dense pieces, softer edges, and natural oil spreading across the surface. Lime juice enters first. It coats the exposed avocado and sharpens the mixture. Salt follows in a measured amount. Chopped cilantro, diced onion, and jalapeno are added as separate streams. The mixer does not whip the avocado into a smooth paste. It folds and presses the flesh just enough to create a thick, chunky mass with visible pieces suspended in a creamy base. The guacamole is portioned into pans or sealed containers. The surface is leveled to reduce air pockets. It remains cold, so the structure stays dense and spoonable. This finished component later moves to the service line as a chilled topping. Tomato salsa follows a different path. Tomatoes are washed and diced into small cubes with sharp rotating blades. The cut must be clean, not crushed. If the tomato breaks down too much, the salsa turns watery. The diced tomatoes drop into a mixing bin with onion, cilantro, jalapeno, citrus juice, and salt. Slow paddles fold the ingredients together while keeping the cubes intact. The salsa becomes bright, wet, and textured. Liquid collects between the pieces, but the mixture still holds visible diced structure. It is transferred into cold pans and covered for holding. The same controlled mixing method is used for other fresh salsa formats, with ingredient size, moisture level, and chili intensity adjusted by the formula. Corn salsa starts with kernels rather than tomatoes. The corn is drained, chilled, and combined with diced peppers, onion, cilantro, citrus juice, and seasoning. The kernels remain separate and glossy. The mixer turns slowly so the corn does not split or become starchy. The finished salsa has a loose, scoopable texture with small pieces distributed evenly through the batch. Lettuce is processed as a crisp, cold component. Whole heads or prepared leaves are trimmed, rinsed, dried, and cut into thin shreds. The cutting blades create long, narrow strips. After cutting, the lettuce passes through drying equipment that removes surface moisture. Too much water would pool in the final bowl or soften tortillas. The shredded lettuce is kept cold and loose. Cheese begins as chilled blocks. The blocks pass through shredding blades that cut them into uniform strands. The cheese must be cold enough to slice cleanly. If it is too warm, it smears against the blades and clumps. The shreds fall into containers as a light pile, then move into cold holding for later topping. Sour cream arrives as a thick dairy component. It is held cold and stirred gently before portioning. The texture must remain smooth and pourable enough to spread across hot fillings, but thick enough to stay in place once added to a burrito, bowl, or taco. While the cold line is prepared, hot components move through their own production flow. Rice begins with dry grains entering a cooking vessel. Water, salt, and oil are added in measured amounts. Heat drives water into the grains. The rice swells as starch gelatinizes inside each grain. The cooker controls steam, moisture, and time so the grains soften without breaking down into paste. After cooking, the rice is fluffed. The movement separates the grains and releases steam. Citrus juice and chopped cilantro are folded in. The paddles turn slowly to avoid crushing the grains. The finished rice is light, moist, and separate enough to scoop cleanly. Beans begin as hydrated black beans or pinto beans. They enter kettles with water and seasoning. Heat softens the skins and thickens the cooking liquid. The beans are not fully mashed. they remain mostly whole, with some starch released into the surrounding liquid. This creates a glossy, thickened texture that coats the beans and helps them hold heat. The beans are transferred into hot holding pans. The liquid level is controlled so they do not dry out. Gentle stirring keeps the solids evenly distributed. Black beans and pinto beans remain separate streams until final assembly. Meat preparation begins with seasoning and marination. Chicken pieces move into a marinade system containing chili-based seasoning, spices, salt, citrus, and oil. The marinade coats the surface and moves into the folds of the meat. The pieces rest under cold conditions until the seasoning is distributed. Steak follows a similar path, but with different handling. The cuts are seasoned and held so the surface absorbs flavor. Barbacoa and carnitas use slower cooking methods that break down connective tissue and create tender, shredded textures. Sofritas begin from tofu, which is cut, cooked, and combined with a spiced sauce until the pieces absorb the seasoning. For grilled chicken, the marinated pieces move onto a hot flat top or grill surface. The lower side sears first. Moisture evaporates rapidly where the meat touches the hot metal. Browning develops on the surface. The pieces are turned so the second side cooks evenly. Heat moves inward until the center reaches the target doneness. The cooked chicken rests briefly so juices stabilize inside the meat. It then moves to cutting. Blades or knives divide the pieces into small cubes. The cut surfaces expose the moist interior, while the browned exterior remains visible on many pieces. The diced chicken transfers into a hot holding pan. Steak is seared on a hot surface in the same mechanical sequence: contact, browning, turning, finishing, resting, and cutting. The steak is sliced or chopped into portions that can be scooped quickly. The finished pieces hold a darker seared surface and a tender interior. Barbacoa uses a slow, moist heat process. Seasoned beef cooks with liquid and spices until fibers separate easily. Once cooked, the meat is shredded. The strands mix with the cooking liquid, creating a juicy, sauced filling. The liquid keeps the meat soft in the hot holding pan. Carnitas is cooked until the pork becomes tender enough to pull apart. The pieces separate into shreds and chunks. The seasoning coats the meat, and the cooking juices hold the texture together. Like barbacoa, it is held hot as a moist filling. Sofritas uses tofu as the base. The tofu is pressed, cut, and cooked to remove excess moisture. It is then combined with a seasoned sauce. The tofu pieces absorb the liquid and become coated with a reddish, spiced layer. The mixture stays soft but not watery. Fajita vegetables begin with peppers and onions. They are sliced into long strips. The strips hit a hot cooking surface with oil and seasoning. Steam rises as moisture leaves the vegetables. The onions soften and become translucent at the edges. The peppers bend, darken in spots, and remain slightly firm. The cooked vegetables move into hot holding. They must remain separate enough to lift with tongs, not collapse into a wet mass. The balance comes from high heat, short cooking time, and controlled holding moisture. Tortillas are prepared just before assembly. Flour tortillas are warmed on a heated press or flat surface. Heat softens the fat and starches inside the tortilla. The disc becomes flexible, warm, and stretchable. A cold tortilla would crack during folding. A properly warmed tortilla bends around fillings without tearing. Corn tortillas for tacos are warmed in stacks or individually. They become pliable and fragrant. Hard taco shells are held dry so their crisp structure stays intact. Moisture is kept away from them until assembly. The assembly line brings all components together in a fixed sequence. For a burrito, the warmed flour tortilla is laid flat. Rice is placed first as a foundation. Beans follow, either black or pinto. Meat or sofritas is added in a central line. The hot fillings sit lengthwise so the tortilla can wrap around them. Salsa is added next. The spooned salsa settles into the rice and meat. Sour cream, cheese, guacamole, lettuce, or fajita vegetables are layered according to the order. Each ingredient changes the structure. Rice absorbs liquid. Beans add softness. Meat adds weight. Cheese and sour cream fill gaps. Lettuce adds volume near the top. The tortilla is folded from the bottom over the filling. The sides fold inward. The cylinder rolls forward, tightening the contents inside. The finished burrito is wrapped in foil. The foil supports the shape and holds the folded seam closed. For a bowl, the container replaces the tortilla as the base. Rice spreads across the bottom. Beans and protein sit above it. Salsas, cheese, sour cream, guacamole, fajita vegetables, and lettuce are layered upward. The bowl format depends on vertical stacking rather than rolling tension. A sharp Nerds candy syrup snaps from liquid to crystal as it coats thousands of tiny rotating sugar centers. Sugar, glucose syrup, water, acid ingredients, flavor components, and color are prepared as separate streams before they meet the candy building equipment. The process depends on layering rather than molding. Nerds do not come from one smooth mold cavity or one stamped sheet. They are built as small, jagged pieces, layer by layer, while moving in rotating pans and drying chambers. The first material is the center. Tiny sugar crystals, or small candy seeds, are screened before coating. The screen removes dust, broken powder, oversized grains, and pieces that would grow unevenly. The accepted centers are small enough to tumble freely, but solid enough to survive repeated coating cycles. The centers enter a rotating coating pan. The pan is tilted, wide and smooth inside. As it turns, the centers climb partway up the wall, then slide and tumble back down. The movement keeps every piece in motion. No piece stays still long enough to become flat on one side. A cooked syrup is prepared in a separate kettle. Sugar and glucose syrup dissolve in water. Heat concentrates the mixture by driving moisture away. The syrup becomes thick, clear, and sticky. It must be fluid enough to spray, but concentrated enough to dry quickly once it lands on the centers. Flavoring and acid are added carefully because Nerds need a sharp, bright taste. The acid gives the candy its tart snap. The flavor component gives each batch its specific fruit character. Color is metered in to match the flavor stream. A grape batch becomes purple. A strawberry batch becomes pink or red. A lemon batch becomes yellow. The syrup moves to spray nozzles aimed into the rotating pan. The nozzles release fine streams or a controlled mist over the tumbling centers. Each center receives only a thin layer. If too much syrup enters at once, the pieces stick together and form clumps. If too little enters, growth becomes slow and uneven. Warm drying air flows through or across the pan. The new syrup layer loses moisture. Sugar crystallizes on the surface. The pieces change from wet and shiny to dry and rough. Then another coating cycle begins. Syrup lands, tumbling continues, air dries the surface, and the pieces grow slightly larger. This cycle repeats many times. The candy does not grow smoothly like a polished jawbreaker. Nerds keep their uneven shape because the centers tumble randomly and the syrup dries in tiny ridges. Edges, bumps, and corners build naturally as layers collect at different points. The sound inside the pan changes during the run. Early centers make a light sandy hiss. As the pieces grow, the pan produces a sharper rattling sound. The candy pieces strike each other with more weight. The stream becomes brighter in color and more irregular in shape. The coating system controls syrup temperature, pan speed, airflow, and batch time. Faster rotation creates more tumbling and separation. Slower rotation gives heavier rolling. Airflow must dry the surface quickly enough to prevent sticking, but not so aggressively that syrup dries before it spreads. After enough layers are added, the batch is discharged from the pan. The candy flows out as a rough mound of colored pieces. It is still warm from drying air and coating. The pieces must cool and stabilize before final sizing. The candy travels through a cooling conveyor or holding bin. Air moves across the pieces. Residual moisture equalizes inside the coating layers. The surface becomes harder and more brittle. The rough texture firms into the crunchy shell associated with nerds. The cooled candy reaches a sizing station. Vibrating screens separate the pieces by dimension. The smallest fragments drop through lower openings. Oversized clusters stay on top and are diverted. The correct size pieces continue forward. This step is important because coating pans naturally create variation. Some pieces grow faster, some remain smaller. Some pieces stick briefly and separate later into unusual shapes. The screen does not make them identical, but it narrows the range so the finished candy pours evenly and crunches consistently. The accepted pieces may pass through a polishing or dust control stage. Light tumbling removes loose sugar dust from the surface. Airflow carries fines away from the product stream. The candy remains rough, but it is not powdery. Different colors and flavors are produced in separate batches. One pan may produce pink pieces. Another may produce purple pieces. Another may produce orange, green, yellow, or blue pieces depending on the finished product format. Each batch follows the same basic coating logic but uses its own syrup color and flavor system. After sizing and dust removal, each flavor moves into a holding hopper. The hoppers feed the blending and packaging system. Gates, at the bottom, release controlled amounts of candy into weighers or metering devices. For a 2-flavor Nerds box, 2 streams are kept separate for most of the process. Each flavor has its own hopper and feed path. The package is designed so the flavors stay divided into separate compartments. This requires precise filling into each side of the box. The paperboard box is formed from flat printed blanks. The blanks feed into a cartoning machine. Folding rails crease the board along pre-scored lines. The box shape forms around mandrels or guides. Glue or locking tabs secure the sides. For a dual compartment box, internal folds create 2 chambers. The center divider must align correctly so the flavors do not mix before opening. The box remains open at the top or at a filling edge while it moves under the candy fillers. The first candy flavor drops into one compartment. The flow is controlled by volume or weight. The pieces fall like tiny stones, clicking against the paperboard. The box advances. The second flavor drops into the opposite compartment. The divider keeps the 2 colored streams apart. Fill accuracy matters because the pieces are small and irregular. A simple liquid filler cannot be used. The system relies on vibrating feeders, small hoppers, timing gates, and check weighing to control how much candy enters each side. Once filled, the box moves to closing. Flaps fold in sequence. Glue spots or tuck closures lock the carton shut. The box must close cleanly without crushing the candy or leaving gaps where pieces could leak out. For theater-sized boxes or larger formats, the carton is bigger, but the logic remains similar. Candy is weighed into the container, flaps close, and the package is sealed. Some formats mix multiple flavors together before filling, while others keep them divided. For bagged Nerds varieties, the candies follow a different packaging route. Multiple flavors may be blended in a rotating drum or on a controlled conveyor. The blend must be even, so one color does not dominate each bag. Vibrating feeders meter each color into the stream at the programmed ratio. The mixed candy enters a multi-head weighing system. Each small weighing bucket receives a portion of candy. The machine calculates which combination of buckets equals the target weight. Those selected buckets open together, dropping candy into the bagger. Three Musketeers bars are built by producing an aerated chocolate nougat center and then coating it in tempered milk chocolate before wrapping. The factory line is arranged so the nougat stream runs continuously into forming and cutting, while the chocolate stream runs continuously through tempering and enrobing. Both streams are tuned to match temperature, viscosity, and throughput, so the coating seals cleanly around the center without sink marks or edge splits. The milk chocolate coating begins with bulk ingredients staged for refining and conching. Granulated sugar is screened to a narrow particle size range so the roller refiner can produce a predictable grind. Cocoa liquor is preheated to lower viscosity and allow accurate pumping into the mixing tank. Cocoa butter is melted in jacketed vessels and circulated through filters to remove any solid crystals that could seed unstable texture. Milk powder is fed from sealed bins and is deagglomerated in a low shear disperser so it hydrates into the fat phase without forming dry nodules. Lecithin is held in a small day tank and is dosed late, so it reduces viscosity after the primary particle size reduction. Vanilla or vanillin is stored as a concentrated liquid and is metered as a final flavor addition to avoid volatilization during extended heat exposure. A premixer combines cocoa liquor, a portion of cocoa butter, and sugar into a thick paste that can be refined. The paste is pumped to a 5-roll refiner, where it is squeezed into thin flakes that fracture sugar crystals and cocoa particles to a controlled fineness. The gap settings on each roll stage determine final particle size distribution, which controls mouthfeel and flow at enrobing. Refined flakes fall into a feed chute that meters into a conch. The conche applies heat and shear to drive off undesirable volatiles and to coat particles with fat. During conching, the remaining cocoa butter is added in increments to reach target viscosity without flooding the mass too early. Milk solids are blended in, so lactose and milk proteins are dispersed uniformly without scorching. Lecithin is added near the end to adjust yield value and plastic viscosity to match curtain requirements at the enrober. After conching, the chocolate enters a holding tank with gentle agitation that prevents separation and keeps temperature stable. From the tank, it flows to a tempering system that builds the correct crystal structure in the cocoa butter. The chocolate is heated to fully melt existing crystals, then cooled through a controlled zone to form stable seed crystals. It is then slightly reheated to remove unstable forms while preserving the stable fraction. The tempered chocolate exits at a narrow temperature band where viscosity is low enough for enrobing yet crystal content is high enough to set quickly on cooling. Inline viscometers monitor flow and trigger cocoa butter trim additions if the chocolate thickens. Filters ahead of the enrober remove stray solids that could block the curtain slot or imprint the coating surface. The aerated center starts as a sugar syrup system designed to whip into a stable foam. Granulated sugar is dissolved in hot water in a steam-jacketed cooker where temperature is driven to a target solids level. Glucose syrup or corn syrup is pumped in to reduce crystallization and to keep the finished nougat soft. The syrup is cooked under controlled pressure, so boiling is efficient and the concentration is repeatable. When the syrup reaches its target, it is discharged through a flash cooling step that drops temperature enough to prevent overcooking while preserving fluidity for mixing. The syrup then enters a continuous aeration mixer where it meets foaming proteins and fat. The foaming phase can be based on egg whites or protein blends that create a thin film around air bubbles. Liquid egg white is filtered and tempered so it whips predictably without breaking. If dried albumin is used, it is rehydrated under high shear and allowed to rest so hydration is complete before aeration. Proteins enter the mixer where high-speed rotors incorporate air while controlling bubble size distribution. Bubble size is managed by rotor speed, back pressure, and viscosity, which together determine the final density of the center. A small amount of fat is introduced to soften texture while not collapsing foam. Emulsifiers are used to stabilize the air cells and reduce drainage of the syrup phase. Cocoa or chocolate flavor components can be blended into the center so the interior tastes like light chocolate rather than plain vanilla. The aeration mixer operates as a pressurized system, so air injection and shear can be controlled precisely. Compressed air passes through sterile filters, then through a mass flow controller that sets the air rate per kilogram of nougat. The mixer creates a continuous foam stream that is metered to the forming section. Density is checked by inline measurement that compares mass flow to volumetric flow. If density drifts, the system adjusts air rate or syrup feed to recover. Temperature of the foam is controlled because warm foam collapses and cold foam stiffens before forming. A heat exchanger may be used on the syrup line to fine-tune final foam temperature at discharge. Once aerated, the nougat is sent to a depositor or extrusion head, depending on the specific forming method. In an extrusion layout, the foam is pushed through a slot die that creates a wide ribbon with a controlled thickness. The ribbon lands on a moving belt that has a release surface to prevent sticking. Belt speed is synchronized to extrusion flow, so thickness stays constant across the width. A leveling roller may follow to flatten the ribbon and to remove surface waves. The ribbon then passes under a conditioning tunnel where temperature is reduced gradually, so structure firms without creating a brittle skin. This conditioning step sets the foam walls enough for clean cutting. The nougat sheet is cut into bars using a guillotine or rotary slitter system. Longitudinal knives create parallel lanes with precise width. A transverse guillotine cuts each lane into individual pieces at the target weight. Knife timing is servo-controlled to keep cuts aligned even if belt speed changes slightly. Scrap from edge trim is collected and recycled back into the aeration mixer in controlled ratios so density remains stable. Bar weight is checked by dynamic scales that weigh each piece at speed. Out of tolerance, bars are removed by air jets that divert them into a rework stream. Before coating, the centers may pass through a brief pre-coat step. A thin layer of chocolate can be applied to reduce moisture migration and to improve adhesion of the final coat. This pre-coat is often applied as a bottoming film or a partial curtain. The centers then enter a short chill zone that sets the pre-coat so the bar can handle the stress of full enrobing. Surface temperature at enrobing is managed because a warm center can thin the coating and cause weak corners. A cold center can cause premature thickening and a rough surface. The line therefore targets a specific center surface temperature that balances flow and setting. Enrobing is performed by sending each nougat center through a chocolate curtain. The tempered milk chocolate flows from a header tank into a curtain slot that produces a uniform sheet of chocolate. The bar passes under the curtain and receives top and side coverage in a single pass. A bottoming wheel or bottomer reservoir coats the underside and closes the seam. Immediately after, coating the bar rides over a vibrating section that removes excess chocolate and levels the coat. Air knives blow controlled air across the surface to thin the layer and to sharpen edges. Air pressure is tuned so it does not expose the nougat at corners. The chocolate runoff is collected and returned to the tempering circuit where it is re-tempered before reuse. Decorative top marks can be added while the coating is still fluid. A striping head deposits thin lines of chocolate across the top to create the characteristic surface pattern. The striping chocolate is tempered separately to match viscosity and to prevent bloom in the stripes. Nozzles are aligned to bar lanes, so stripes land consistently. Flow is controlled by servo pumps that pulse for each bar group. Stripe height is kept low, so it does not crack during cooling or wrapping. After enrobing the bars, enter a cooling tunnel that sets the chocolate crystal network. Cooling is staged in zones to control contraction and gloss. An initial zone cools gently so the surface does not freeze before the interior sets. A middle zone cools more strongly to lock in crystal structure and to prevent deformation. A final zone equalizes temperature so the bar exits without condensation risk when exposed to ambient air. Conveyor speed and tunnel temperature define residence time. If residence time is too short, the coating remains soft, and fingerprints during handling appear as dull marks. If residence time is too long, the bar can overcontract and pull away at the seam. Kit Kat bars are manufactured by building crisp wafer sheets in continuous ovens, then layering them with fat-based cocoa cream before cutting fingers and enrobing them in tempered chocolate. The line is designed so wafer output is buffered to match chocolate throughput. The process starts with a batter system tuned for rapid baking and controlled porosity. Wheat flour is conveyed from silos to a sifter that removes bran specks and compacted lumps. The sifted flour drops into a day bin that feeds a high-speed whey hopper. Cornstarch may be blended into the flour stream to reduce gluten development and to increase snap after baking. Leavening is dosed in small quantities because wafer rise must be minimal and uniform. Salt is metered finely so it dissolves fully in the batter water phase. Sugar is used at a lower level than cake because wafer structure relies on starch gelation and moisture removal rather than sweetness. Liquid water is tempered to stabilize viscosity and to prevent seasonal drift in batter flow. Vegetable oil or melted fat is held in jacketed tanks and pumped with gear pumps for repeatable dosing. Emulsifiers are added to improve plate release and to help the batter spread thinly across hot surfaces. A portion of batter may include recycled wafer trim ground to a fine meal and hydrated to keep waste low without adding grit. Batter mixing is performed in a continuous mixer or in a batch mixer with rapid turnover, depending on line scale. Dry ingredients are blended first, so leavening and salt are dispersed before liquids arrive. Liquids enter through multiple injection points, so flour hydration occurs quickly without dry pockets. The mixer uses high shear at the inlet and lower shear near discharge to avoid excessive gluten formation. Batter temperature is controlled because warm batter thins and overspreads, while cold batter thickens and causes uneven fill. Viscosity is measured by inline torque or pressure drop and adjusted by microdosing water. A deaeration step may follow mixing to remove large bubbles that would create blisters in the wafer sheet. The finished batter is pumped to a feed manifold that supplies the baking machine with constant head pressure. Wafer baking uses paired heated plates that close to a precise gap and imprint a grid texture. The plates are heated by gas burners or thermal oil circuits and are held within tight temperature tolerances across the surface. Batter is deposited onto the lower plate by a dosing head that measures volume for each plate cavity. The top plate closes and spreads the batter into a thin layer that fills the pattern relief. Baking begins instantly as water flashes into steam and the starch begins to set. The plate set moves through a tunnel oven where heat continues to drive moisture out while browning remains controlled. Venting removes steam so it does not condense on cooler machine sections and drip onto new plates. Plate pressure and gap determine wafer thickness, which later determines finger count per bar and final snap. Bake time is tuned so moisture drops low enough for crispness, yet not so low that the sheet becomes brittle during handling. When plates open, the baked wafer sheet releases and is transferred onto a cooling conveyor. The sheet passes under fans that equalize temperature and prevent trapped heat from softening the crisp matrix. Sheet moisture is measured indirectly by near-infrared sensors that scan across width. Any drift triggers changes in oven speed or plate temperature to recover the target. Wafer sheets are fragile, so conveyors use low impact transfers and short drops. Alignment guides keep sheets square for the next operation. Scrap edges and broken sheets are separated and routed to a grinder for controlled reuse. Layering begins with preparation of the cocoa cream that bonds wafer sheets into a multi-layer block. This cream is a fat continuous paste rather than a water-based filling. Sugar is milled to a fine powder and blended with cocoa powder to form a dry premix. Cocoa butter and vegetable fats are melted and filtered to remove crystals that would make the paste grainy. The dry premix is added into the melted fat in a mixing tank with strong agitation. The mixture then passes through a roll refiner or bead mill to reduce particle size and to improve spreadability. Lecithin is added late to reduce viscosity and help the paste wet the wafer surface quickly. Flavor is added at the end to preserve volatile notes. The finished cream is held in a jacketed buffer tank at a temperature that keeps it fluid but not so hot that it seeps deeply into wafer pores. Cream application uses a spreader system with metering rollers. A wafer sheet enters the station and passes under a curtain or roller that lays down a precise film thickness. The film thickness is controlled by roller gap and by paste viscosity. Another wafer sheet is placed on top by a pick and place unit that aligns edges. The sandwich passes through a compression section that ensures full contact without crushing the wafer cells. This layering repeats to build a block with multiple wafer layers separated by thin cream layers. The number of layers determines the final finger height and bite. Registration is critical because misalignment causes exposed wafer steps after cutting and uneven coating. After stacking, the wafer block enters a setting tunnel where the cream partially crystallizes to lock layers together. Temperature is reduced in stages to avoid warping from rapid contraction. The block is supported on a flat belt to maintain planarity. Block hardness is monitored by deflection sensors that measure how much the block bends at a given support span. When the block reaches a target firmness, it moves to cutting. If the block is too soft, blades smear the cream and pull crumbs. If the block is too hard, blades chip wafer edges and create dust. Cutting converts the block into long logs and then into fingers. A first set of rotary knives or ultrasonic blades slices the block lengthwise into bars that match the finger group width. Blade spacing is adjustable for different formats, like 2-finger or 4-finger packs. A second cutter slices the bars into individual finger lengths. Blade timing is synchronized to belt motion to prevent diagonal cuts. Crumb extraction hoods collect wafer dust so it does not contaminate chocolate surfaces later. Trim pieces are segregated because they can be reworked into wafer meal or into cream base depending on quality. The cut fingers are transferred gently to avoid cracking along the wafer grid. Before enrobing, the fingers may receive a base coat to improve seam closure. A bottoming bath lays chocolate onto the underside as the finger rides over a wheel. The wheel transfers a film and then excess is wiped to a controlled thickness. The pre-coated fingers pass through a short cooling zone so the base sets enough to support the full coat. Surface temperature is controlled because warm fingers thin the chocolate layer and cold fingers cause thick buildup at edges. Chocolate coating starts with production of the milk chocolate used for the shell. Sugar, cocoa liquor, cocoa butter, and milk solids are mixed and refined to a target particle size. Refining is done on roller refiners that produce flakes for conching. Conching applies heat and shear to coat particles with fat and to reduce harsh notes. Lecithin is added to tune flow for enrobing and to reduce yield stress. The chocolate is then tempered to create stable cocoa butter crystals. Tempering follows a melt-cool reheat profile and is controlled by temperature sensors and viscosity feedback. The tempered chocolate is held in a header tank that feeds the enrober curtain at constant pressure. Enrobing covers the wafer fingers with a continuous curtain of tempered chocolate. Each finger passes through the curtain and gets top and side coverage. A bottoming section ensures the underside is sealed and eliminates bare spots at the edges. Vibrating conveyors level the coating and release trapped air at corners. Air knives shape the final thickness and clear chocolate from the finger grooves where excess would bridge the separations. Runoff chocolate is collected and returned to the tempering loop so crystal structure remains correct. Some formats add a chocolate line between fingers to strengthen the breakpoints, and this is done by targeted deposition nozzles before final cooling. Cooling tunnels set the coating without causing bloom or warping. The tunnel is divided into zones that control the rate of crystal growth. Early cooling stabilizes the surface gloss. Middle cooling builds strength through the thickness. Final conditioning equalizes temperature so wrappers do not trap condensation. Conveyor speed sets residence time and is matched to coating thickness. If cooling is too aggressive, the chocolate contracts unevenly and can crack at the corners. If cooling is too mild, the coating stays soft and picks up belt marks. Snickers bars are assembled as a layered composite where a whipped nougat base is topped with roasted peanuts and caramel, then sealed in a tempered milk chocolate shell. Production begins by building ingredient streams that can run continuously at matched flow rates. Each stream is conditioned for temperature and viscosity so it can be deposited or extruded with stable geometry. The final bar depends on tight control of moisture because nougat must stay soft while caramel remains pliable and peanuts remain crisp. Milk chocolate for the outer shell is prepared first because it requires refining conching and tempering steps that run best as steady-state operations. Sugar is screened to remove hard lumps and to maintain consistent grind behavior. Cocoa liquor is warmed to reduce viscosity before blending. Cocoa butter is melted and filtered so the fat phase is uniform and free of seed crystals. Milk powder is sifted and deagglomerated to prevent specking in the finished coating. The ingredients enter a pre-mixer that produces a thick paste with evenly wetted solids. This paste is refined on roller mills or stirred media mills to reach a target particle size that balances smoothness with coating flow. Refined chocolate flakes drop into conchis where heat and shear coat particles with fat and drive off unwanted volatiles. Additional cocoa butter is added in stages, so viscosity is lowered without losing shear efficiency in early conching. Lecithin is added late to reduce yield stress and to improve curtain formation at the enrober. Flavor is added near the end, so aromatic compounds are not stripped by long residence at temperature. After conching, the chocolate is held in insulated tanks with slow agitation to prevent separation. The chocolate then enters a tempering machine that establishes a stable cocoa butter crystal form. Tempering runs in a melt-cool reheat profile where all existing crystals are first removed, then stable seed crystals are created, then unstable forms are melted out. The tempered chocolate exits at a narrow temperature window that is tuned to the enrober and to the cooling tunnel profile. Inline viscosity measurement checks for drift caused by temperature change or solid shift. If viscosity rises, the system trims with cocoa butter or adjusts temper temperature to recover flow. Chocolate is filtered before enrobing to prevent curtain streaks and to remove any particles that could block the slit. Nougat manufacturing begins with a cooked syrup that will be whipped into a low-density foam. Sugar is dissolved in water in a continuous cooker that controls concentration by temperature and flow. Glucose syrup is added to reduce sucrose crystallization and to keep the finished nougat tender. The syrup is cooked to a target solids level that defines final chew and shelf stability. The hot syrup is discharged through a heat exchanger that drops temperature to the range needed for mixing without oversetting. The syrup then feeds into a continuous aeration mixer where it meets proteins and fat. The protein phase can use egg albumin or alternative foaming proteins, depending on formulation. If liquid egg white is used, it is filtered and tempered for predictable whipping. If dried albumin is used, It is rehydrated under controlled shear, then rested to complete hydration. Proteins enter the mixer, where rotors incorporate air and create a stable bubble network. Bubble size is controlled by rotor speed and by back pressure at the discharge. Fat is added in a controlled stream to soften the foam walls and to improve chew without collapsing aeration. Emulsifiers stabilize the air cells and reduce drainage of syrup from the foam. Salt and flavor are added as concentrated solutions so they disperse instantly. The nougat exits as a continuous ribbon whose density is measured in line by mass flow and volumetric flow correlation. Nougat forming is commonly done by extrusion onto a moving belt. The extruder head uses a slot die to shape a wide sheet at a defined thickness. The belt speed is synchronized to extruder throughput, so sheet weight per length stays constant. A leveling system flattens the sheet and removes surface waves that would later telegraph through caramel. The nougat sheet enters a conditioning tunnel where temperature is reduced gradually to strengthen the foam network. The aim is to reach a firmness that supports topping without squeezing out air. If the sheet is too warm, peanuts sink and caramel spreads unevenly. If the sheet is too cold, the surface cracks under rollers and causes delamination after cutting. Caramel production runs in parallel because caramel requires controlled cooking and controlled final water content. Sugar and glucose syrup are blended and heated in a continuous caramel cooker. Milk or dairy solids are added depending on flavor and color targets. Fat is added to adjust chew and to reduce sticking during deposition. The cooker uses staged heating so the mixture rises to cooking temperature without scorching solids. Final concentration is achieved by driving off water to a precise solids level, which controls viscosity and final bite. The caramel exits through a flash cooler or scraped surface heat exchanger that reduces temperature while maintaining flow. The cooled caramel is held in a heated buffer tank with slow agitation that prevents skin formation and keeps temperature uniform. Viscosity is monitored because caramel that is too thin will flow off the nougat, and caramel that is too thick will not encapsulate peanuts properly. Peanut preparation is another parallel stream because the bar relies on a high fraction of nuts with stable texture. Raw peanuts are cleaned by screens and air aspiration to remove light debris. They are then graded by size, so the topping layer has consistent packing density. Roasting is performed in continuous roasters where time and temperature control drive flavor, development, and final moisture. After roasting, peanuts are cooled quickly to stop carryover heating and to preserve crispness. If salted peanuts are used, a fine salt solution or dry salt is applied in a tumbler and is then set by brief drying. Peanuts are then conveyed to a distribution hopper that feeds the topping system at constant rate. Vibratory feeders control flow and prevent bridging in the hopper. Layer assembly starts when the conditioned nougat sheet reaches the caramel deposition station. A spreader head or curtain depositor lays a uniform caramel layer across the nougat surface. Thickness is controlled by depositor slot gap and by pump speed. The caramel layer must be thick enough to bind peanuts and to form the characteristic chew band. Immediately after caramel application, peanuts are distributed across the surface. A scatter system uses vibrating trays and patterned gates to place peanuts evenly without bare zones or piles. A light compression roller follows to press peanuts into the caramel so they are partially embedded. Roller pressure is tuned so peanuts seat without crushing and without forcing caramel to the edges. Excess peanuts are vacuumed or brushed off and recycled back to the topping hopper. The layered slab then enters a cooling and setting section that fixes layer geometry before cutting. Temperature is reduced to set caramel viscosity and to lock peanut position. Cooling is staged because sudden chilling can create internal stress that later causes layer separation. The slab is supported to prevent sag because caramel remains soft for a period. Sensors track slab temperature at surface and core because the slab is thick and cools slowly. Once the slab reaches the target firmness, it moves to slitting and cutting. Slitting divides the wide slab into lanes that match the final bar width. Rotary knives cut lengthwise and are adjusted to maintain clean edges through peanuts and caramel. Knife design is selected to handle nuts without chipping and without dragging caramel. Crumb and nut fragments are extracted to keep the line clean and to prevent inclusions in the chocolate coat. The lanes then pass to a guillotine cutter that cuts each lane into bar lengths at high speed. Cut timing is servo-controlled to match belt speed and to maintain consistent length. Off-size bars are diverted by a reject gate and are routed to rework streams, where they can be remelted into nougat or caramel depending on composition. Before enrobing many lines, apply a thin pre-coat or bottom coat to improve seal quality. A bottoming bath coats the underside and forms a base layer that helps close seams during full enrobing. The base coat is set briefly in a short cooling zone so the bar can be handled without smearing. This step also reduces exposure of nougat at the bottom corners, where enrober curtains can thin. Bar surface temperature is then brought to the target for full coating because temper performance depends on the heat load from the centers. Fresh strawberries arrive in bulk containers and are immediately transferred onto vibrating sorting tables. The surface trembles in rapid pulses, spreading the fruit into a single layer. Optical scanners sweep across the moving belt, detecting color density and surface irregularities. Jets of compressed air fire in milliseconds, ejecting underripe or bruised berries. The selected strawberries continue forward in a uniform stream. The fruit drops into a rotating drum washer. High-pressure sprays strike from multiple angles, stripping away soil and field residue. The drum slowly turns, ensuring every surface is exposed to the water jets. Excess water drains through perforations while the berries advance toward the discharge chute. A final mist rinse removes remaining particles before the fruit exits onto a dewatering conveyor lined with absorbent rollers. Next, the strawberries pass beneath stainless steel blades that remove stems with precise vertical cuts. The trimmed berries fall into a stainless hopper feeding an industrial crusher. Inside the crusher, rotating paddles press the fruit against a perforated screen. The flesh collapses into a thick pulp, releasing juice and seeds. The sound shifts from a soft tumble to a wet grinding hum as the texture transforms into a uniform mash. The pulp moves into a heated processing tank equipped with a slow-turning agitator. Granulated sugar is metered in through a screw feeder. The agitator sweeps through the mixture, dissolving sugar crystals into the strawberry mass. Gentle heat intensifies the aroma while evaporating excess moisture. The mixture thickens slightly as soluble solids increase. A refractometer probe continuously measures sugar concentration, adjusting feed rates to reach precise sweetness. Once balanced, the strawberry blend flows through a fine mesh filter. Seeds and fibrous fragments are separated, producing a smooth puree. The filtered puree enters a vacuum deaerator, where trapped air bubbles rise and collapse under reduced pressure. The surface briefly foams, then settles into a glossy, uniform liquid. This step prevents oxidation and preserves the bright red hue. Parallel to fruit preparation, the dairy base begins in large insulated tanks. Fresh cream and whole milk are pumped in controlled proportions through stainless pipelines. Load cells beneath the tanks monitor weight to ensure exact ratios. Liquid sugar syrup joins the blend through automated valves, eliminating undissolved crystals. The mixture swirls under high-speed agitators, forming a homogeneous liquid. Milk solids and stabilizers are introduced through a powder induction system. Fine. Powders are drawn into the vortex created by the spinning mixer, preventing clumping. The stabilizers hydrate gradually, thickening the base and improving body. The sound of the mixer deepens as viscosity increases. Temperature sensors regulate the mixture to maintain optimal hydration conditions. The blended dairy base is pumped into a plate heat exchanger for pasteurization. Thin layers of liquid flow between heated stainless plates. Hot water circulates on the opposite side, raising the temperature rapidly. The mixture reaches pasteurization temperature within seconds and is held briefly in a holding tube. This precise thermal treatment eliminates unwanted microorganisms while preserving flavor integrity. Immediately after heating, the mixture travels back through the heat exchanger, where chilled water cools it down quickly. The rapid drop in temperature prevents overcooking. The base exits at a cold, controlled temperature and flows into aging tanks. Inside these tanks, slow, paddles rotate gently, preventing separation while allowing fat molecules and proteins to stabilize. Over several hours, the mixture thickens slightly as fat crystallizes and stabilizes fully hydrate. Once aged, the dairy base is directed toward a high-pressure homogenizer. The liquid is forced through microscopic openings under intense pressure. Fat globules shatter into tiny droplets, dispersing evenly throughout the mixture. The texture becomes smoother and more stable. The transformation is audible as a sharp hiss accompanies the sudden pressure release. The homogenized base and the prepared strawberry puree converge in a blending tank. Automated flow meters synchronize their entry to achieve the desired fruit concentration. As they merge, rotating blades fold the red puree into the pale dairy liquid. The color shifts from off-white to a uniform pink. The mixture thickens slightly as fruit solids integrate with the cream structure. The combined mixture flows into a continuous ice cream freezer. Inside the cylindrical freezing barrel, refrigerant circulates around the outer shell, drawing heat away rapidly. A dasher spins within the barrel, scraping frozen layers from the inner wall. The scraping action prevents large ice crystals from forming. Simultaneously, controlled air is injected into the mixture. Tiny air bubbles disperse evenly, increasing volume and creating a light texture. As the mixture churns, it transforms from liquid to semi-solid. The texture resembles soft snow. Temperature probes monitor the freezing point continuously. The dasher blades slice through the thickening mass with rhythmic precision, producing a steady mechanical hum. Within minutes, the ice cream reaches a soft serve consistency and is extruded from the barrel through a nozzle. For varieties containing strawberry pieces, an inclusion feeder introduces diced fruit at this stage. The small cubes drop into the flowing stream and are folded gently by a low-speed auger. The movement distributes the pieces evenly without crushing them. Bright fragments remain suspended in the creamy matrix. The semi-frozen ice cream moves through insulated pipes into filling machines. Containers travel along a conveyor beneath multi-nozzle fillers. Each nozzle descends and releases a measured volume. The soft ice cream spirals into the container, forming layered folds. Vibrating plates beneath the conveyor remove trapped air pockets and level the surface. Lids are placed automatically by a rotary placer. A brief downward press seals each container. Date codes are printed in precise black ink on the lid surface. The filled units advance into a hardening tunnel. Inside, powerful fans blast air at extremely low temperatures. The air circulates at high velocity, stripping remaining heat from the product. During hardening, ice crystals stabilize into a fine structure. The temperature at the core drops steadily until the entire mass becomes firm. The transformation locks in the overrun and prevents structural collapse. The containers exit the tunnel, solid and rigid. They pass through a metal detection system that scans each unit for metallic fragments. A reject arm removes any container that fails the scan. Approved units continue to a cartoning station where multiple containers are grouped and wrapped in printed sleeves. Mechanical arms fold cardboard around the stack with crisp, angular movements. The cartons move onto a palletizing line. Robotic arms lift entire layers and stack them with geometric precision. Each layer aligns perfectly, forming a stable cube. Stretch film wraps tightly around the stacked load, binding it into a single secure mass. Before storage, samples from each batch are tested in a texture analyzer. A probe presses into the frozen ice cream, measuring resistance and consistency. The data confirms proper freezing and air incorporation. Color sensors verify uniform pink tones, ensuring the strawberry dispersion is consistent. Throughout the entire process, stainless steel pipelines connect every stage. Pumps pulse rhythmically, maintaining continuous flow. Valves open and close in timed sequences controlled by automated systems. Digital panels display temperatures, pressures, and flow rates in real time. Each transformation occurs in a precise order, from raw fruit and liquid dairy to aerated frozen structure. The final packaged strawberry ice cream rests in cold storage at stable sub-zero temperatures. Inside each sealed container, microscopic ice crystals, evenly distributed air cells, stabilized fat droplets, dissolved sugars, and concentrated strawberry solids form a balanced matrix. The journey from whole berries and fresh cream to smooth frozen dessert is defined entirely by controlled motion, measured heat exchange, rapid freezing, and exact mechanical coordination. Raw milk is delivered to the processing facility in insulated stainless steel tanks. Upon arrival, the milk is passed through a series of mesh strainers to remove any large particulate matter. It then flows into a balance tank, where load cells continuously measure the volume and ensure accurate downstream processing. The temperature of the milk is monitored by inline thermocouples, confirming it is within a range suitable for further processing. The milk proceeds to a clarification step. High-speed centrifuges spin at thousands of revolutions per minute, using centrifugal force to separate any remaining somatic cells, small debris, or micro-impurities. Clarified milk exits the centrifuge through a continuous discharge system, maintaining a smooth, consistent flow. The removal of these particles ensures uniformity in subsequent heating and fermentation stages. Next, the milk enters a standardization phase. Skim and cream fractions, measured precisely by flow meters, are blended to achieve the desired fat content for Greek yogurt. The mixture passes through automated mixers that homogenize the dairy liquid, dispersing fat droplets uniformly to prevent separation and ensure a smooth, final texture. Homogenization is critical for creating a thick, creamy mouthfeel after fermentation and straining. The standardized milk then undergoes pasteurization. It flows through a plate heat exchanger, where thin layers of milk pass between heated stainless steel plates. Hot water, or steam, circulates on the opposite side, rapidly raising the temperature to a controlled level, typically around 85 to 90 degrees Celsius. The milk is held at this temperature in a holding tube for several seconds to destroy pathogenic bacteria and deactivate enzymes. Pasteurization ensures safety and stabilizes proteins for improved coagulation. Immediately after pasteurization, the milk is cooled rapidly via the same heat exchanger in counterflow, using chilled water or glycol to bring it down to the fermentation temperature, typically around 42 to 45 degrees Celsius. Rapid cooling prevents overcooking the proteins and preserves a neutral flavor profile, readying the milk for bacterial culture inoculation. The milk then flows into fermentation tanks. Starter cultures containing specific strains of Lactobacillus bulgaricus and Streptococcus thermophilus are introduced in measured doses. Automated dosing systems ensure exact quantities of active cultures are dispersed evenly. The milk is gently agitated to distribute the bacteria uniformly without creating excessive air bubbles, which could interfere with texture development. Fermentation begins as the tank is held at controlled temperature. Heating jackets or circulating water jackets maintain constant warmth. The bacteria metabolize lactose into lactic acid, gradually lowering the pH of the milk. As acidity increases, casein proteins destabilize and aggregate, forming a gel network. The process is monitored via inline pH sensors, which track the decrease in pH toward the target range, typically between 4.5 and 4.6. During fermentation, slow, intermittent stirring ensures uniform heat distribution and prevents a dense skin from forming on the surface. The gel forms gradually, transforming the liquid milk into a soft, viscous curd. The curd's elasticity is assessed through viscometers or occasional manual sampling to determine the readiness for straining. After the curd reaches the desired acidity and consistency, fermentation ceases by cooling. The tanks are chilled using recirculated cold water or brine jackets, rapidly bringing the yogurt to around 4 degrees Celsius. Cooling halts bacterial activity, stabilizes the gel network, and prevents over-acidification. The cooled yogurt now has a creamy, spoonable texture, but is still high in whey content compared to traditional Greek yogurt. The next stage is straining, which is critical to producing Greek yogurt's characteristic thickness. The yogurt is pumped into centrifugal separators or stainless steel sieves equipped with fine mesh filters. Mechanical pressure or centrifugal force separates liquid whey from the solid curd. In some systems, vacuum-assisted filtration accelerates whey removal while maintaining the integrity of the protein matrix. The result is a dense, creamy yogurt with concentrated milk solids. For large-scale production, the strained yogurt may pass through multiple sequential centrifuges or filters to achieve the target consistency. Each stage incrementally removes whey, reducing moisture content and increasing protein concentration. The sound of liquid passing through perforated plates and the gentle hum of centrifugal rotors indicate continuous separation. Monitoring instruments track moisture levels and protein content to ensure consistency batch to batch. After straining, the thickened yogurt may be blended briefly to homogenize texture. Low shear paddle mixers fold the curd gently, eliminating pockets of firmer or looser gel while avoiding aeration that could introduce unwanted air bubbles. The texture at this point is dense but smooth, with a uniform pale white color. If flavoring or fruit inclusions are desired, they are introduced in a separate blending stage. Natural fruit purees, syrups, or flavor extracts are metered into the thick yogurt using precision dosing pumps. Rotating augers fold these additives gently, maintaining the yogurt's viscosity while achieving even distribution. Inline mixing sensors ensure consistent blending without breaking the gel network. The yogurt then moves to filling equipment. Containers travel along conveyors beneath precision nozzles that deposit exact volumes. The yogurt flows in a continuous stream or spirals into the containers, forming a smooth surface. Vibrating platforms may gently level the yogurt and remove trapped air bubbles, preventing voids that could affect shelf appearance and texture. Filled containers pass through automated capping systems. Lids are sealed with controlled pressure, ensuring airtight closure. Date coding machines print batch information directly on the lid surface. The sealed units are then conveyed into cold storage chambers. Rapid cooling continues as the yogurt is brought down to storage temperature, typically around 0 to 4 degrees Celsius. This step further stabilizes texture, slows bacterial activity to preserve shelf life, and maintains product integrity during handling. Temperature-controlled conveyors and chill tunnels ensure minimal fluctuation, maintaining the thick, creamy structure of the Greek yogurt. Throughout the production line, stainless steel pipelines connect tanks, filters, and filling machines. Pumps regulate flow rate, while automated valves open and close in precise sequences. Sensors continuously monitor flow, temperature, pH, and protein content, providing real-time data to the control system. Any deviation triggers adjustments to maintain consistent product quality. During quality control, samples are drawn from various points along the line. Rheometers measure viscosity, ensuring the yogurt meets textural specifications. Moisture analyzers confirm the whey content aligns with Greek yogurt standards. Colorimeters check for uniformity in hue and brightness. Microbiological tests verify that bacterial counts are within acceptable ranges, confirming proper fermentation and pasteurization effectiveness. The final product exhibits a dense, creamy texture with minimal whey separation. Protein concentration is high, a result of controlled straining and careful homogenization. The yogurt retains a subtle tang from lactic acid development and, if included, uniform fruit dispersion or flavor infusion. Containers are stacked and wrapped for storage, ready to maintain their structure until distribution. Robotic palletizers lift layers of containers and stack them with precise alignment. Stretch film wraps the pallet, securing it for cold transport. Throughout handling, the Greek yogurt remains chilled, preventing separation or texture degradation. Each pallet holds hundreds of containers, reflecting the cumulative precision of pasteurization, fermentation, straining, blending, and packaging. Every stage of the process emphasizes mechanical control and precision. From raw milk clarification through homogenization, controlled fermentation, whey removal, and final packaging, the production relies on continuous monitoring of temperature, pH, viscosity, and moisture. The interplay of mechanical devices, centrifuges, mixers, heat exchangers, pumps, and filling machines ensures consistency, texture, and protein concentration in every batch. The journey from liquid milk to thick, creamy Greek yogurt is defined by sequential transformations: purification, fat standardization, heat-induced protein denaturation, bacterial fermentation, gel formation, controlled cooling, whey separation, and gentle blending. Each transformation is quantified and monitored, producing a stable, high-protein yogurt with characteristic density and smoothness. Even at microscopic scale, the structure is precise. Fat. Droplets are homogenized and dispersed. Protein networks form consistent matrices, and tiny air pockets are minimized. Whey removal concentrates solids without fracturing the gel. The final yogurt exhibits uniform texture, flavor, and acidity due entirely to controlled mechanical and thermal processes. Mascarpone cheese arrives in insulated tanks and is first examined for temperature and consistency. The cheese is pumped through stainless steel pipelines into a blending vat. High shear agitators rotate within the vat, dispersing the dense cheese uniformly and ensuring no lumps remain. The mixers are equipped with variable speed motors, allowing precise control of shear forces to maintain the creamy texture without aerating excessively. Load cells beneath the vat monitor the mass of cheese entering the mixer to confirm exact quantities for recipe consistency. Egg yolks are separated mechanically using rotary egg breaking machines. The eggs are cracked, and yolks and whites are divided using centrifugal separators. Yolks are collected in stainless steel hoppers and gently pumped to pre-blending tanks. Inline viscometers monitor the viscosity of the yolk stream, ensuring smooth, homogeneous flow before incorporation. Sugar is introduced via screw feeders, passing through heated hoppers to prevent clumping. Paddle agitators fold the sugar into the yolks gradually, allowing partial dissolution and formation of a light, smooth custard base. The mascarpone is folded into the yolk-sugar mixture using low-speed planetary mixers. Rotating arms sweep through the mixture, gently folding the dense cheese into the custard without incorporating air. Sensors track torque on the mixer shafts, providing data on viscosity progression. Once fully integrated, the mixture has a uniform, glossy appearance and a controlled thickness that will later allow it to layer effectively in the final dessert. Separately, espresso coffee is brewed continuously. Water is pumped into high-pressure stainless steel extraction units at precisely 92 to 95 degrees Celsius. Ground coffee is metered into portafilters or drum roasters, compacted by mechanical tampers. Pressurized water flows through the grounds at a controlled rate, extracting soluble solids and aromatic compounds efficiently. The resulting espresso flows into holding tanks equipped with heat jackets to maintain temperature until required for soaking. A continuous conveyor system moves the espresso from brewing to the soaking station with minimal exposure to air, preserving flavor integrity. Optional liqueurs, such as coffee-flavored or almond-based spirits, are stored in temperature-controlled tanks. Flow meters regulate the addition of liqueur to the espresso in mixing tanks. Static mixers create a homogeneous coffee liqueur blend, maintaining precise flavor ratios. The mixture passes through inline thermometers, ensuring it is at a temperature that will saturate the ladyfinger biscuits without prematurely softening them. Ladyfinger biscuits are produced separately. Flour, sugar, eggs, and leavening agents are combined in a high-speed mixing ribbon or planetary mixer. The batter's viscosity is monitored by inline rheometers to ensure it is thick yet pourable. Once mixed, the batter is extruded through nozzle systems onto conveyor belts in uniform finger shapes. The fingers pass through tunnel ovens with controlled zones of convection and infrared heating, baking them to a firm yet spongy consistency. Cooling conveyors allow the biscuits to reach ambient temperature while retaining flexibility for soaking. The cooled ladyfingers are transferred to an automated soaking line. Conveyors align the biscuits in single layers beneath nozzles that dispense measured volumes of coffee liqueur mixture. The liquid jets impact the biscuit surface precisely, soaking the exterior without disintegration. Vibrating trays under the nozzles gently shake the biscuits, promoting uniform absorption. Sensors track moisture content in real time, adjusting nozzle flow rates and conveyor speed to achieve consistent saturation across all units. After soaking, the biscuits are deposited into filling trays by robotic arms or gravity-fed systems. The trays are designed with cavities corresponding to the final product size. Each cavity receives a layer of soaked ladyfingers, forming the base layer of the tiramisu. Sensors confirm correct placement, detecting misaligned or broken biscuits, which are automatically removed from the line. The mascarpone yolk sugar mixture is then transferred to depositing machines. Multi-nozzle filling heads extrude precise amounts over the biscuit base. Linear actuators and programmable logic controllers coordinate nozzle motion to spread the mixture evenly. Low-speed paddles may be used after deposition to smooth the layer without incorporating air, preserving the dense, creamy texture characteristic of tiramisu. If multiple layers are required, the process repeats. Another layer of soaked ladyfingers is added atop the mascarpone layer, followed by additional cheese mixture deposition. Robotic arms and precision conveyors ensure exact alignment of layers, avoiding displacement or uneven thickness. Inline laser sensors monitor height and uniformity across the tray, signaling adjustments in deposition volumes to maintain consistency batch to batch. Cocoa powder application occurs once all layers are complete. Fine mesh sifters deliver a controlled dusting of cocoa over the surface. Pneumatic shakers or vibrating plates assist in evenly distributing the powder, preventing clumping or excessive coverage. In large-scale production, automated dispensing heads move across the tray to maintain a uniform layer of cocoa, forming the characteristic top finish of the tiramisu. Color sensors verify the evenness and intensity of the cocoa layer. Completed trays proceed to refrigeration tunnels. Cold air circulates at high velocity, rapidly bringing the product down to approximately 4 degrees Celsius. The cooling process is gradual enough to preserve the gel structure of the mascarpone layer, but fast enough to stabilize moisture in the ladyfingers. Fans and airflow deflectors maintain uniform temperatures across trays, preventing condensation or uneven chilling. During storage and transport, trays remain in temperature-controlled environments. Sensors monitor core temperatures to ensure the mascarpone mixture remains firm without freezing. Refrigerated conveyors maintain orientation and prevent tilting, which could disrupt layered structure. Shock-absorbing supports minimize vibrations, preserving the integrity of delicate layers during handling. Before packaging, automated vision systems inspect each tray. Cameras detect layer uniformity, surface smoothness, and cocoa distribution. Deviations beyond preset tolerances trigger removal or correction of the tray. This ensures that the visual appearance aligns with specifications. Weight sensors confirm that each tray contains the correct mass of ingredients, compensating for minor variations in deposition or biscuit absorption. Once inspection is complete, trays move to sealing stations. Transparent film or lids are applied using mechanical arms with pneumatic actuators. Vacuum or controlled atmosphere sealing may be applied in some systems to extend shelf stability without altering texture. Labeling machines print batch codes, production dates, and other required data on lids or shrink sleeves, using high-resolution thermal printers synchronized with conveyor motion. Finished and packaged tiramisu trays are then conveyed to palletizing robots. Each layer of trays is stacked systematically, maintaining geometric stability. Stretch film is applied in tight spirals around the stack to secure pallets for refrigerated storage. Temperature and humidity sensors within the storage area ensure that the dessert maintains optimal conditions until distribution. Refrigerated transport. Systems continue this temperature-controlled environment, preserving texture, flavor, and visual quality. Throughout production, stainless steel pipelines connect each step: cheese preparation, egg blending, coffee brewing, biscuit soaking, layering, and packaging. Pumps regulate flow, while automated valves control timing and volume precisely. Temperature probes, viscosity meters, pH sensors, and weight scales provide real-time data to the central control system, allowing fine adjustments in process parameters without manual intervention. Each transformation, from raw cheese and eggs to layered cocoa top dessert, relies on precise mechanical and thermal control. Optional flavor modifications, such as chocolate shavings or alternative liqueur blends, are introduced at designated stages using metered dispensers. High-speed augers fold additives into the mascarpone mixture without breaking the gel, ensuring uniform distribution. When applied to the surface, sprinkling systems position toppings precisely without disturbing the layers below. Quality assurance tests occur at multiple stages. Rheometers evaluate the spreadability and firmness of the mascarpone mixture. Moisture analyzers verify that ladyfingers retain enough liquid to be soft but not soggy. Refractometers measure sugar concentration in both the custard and coffee liqueur blend. Visual inspection ensures color consistency, and spot microbiological sampling confirms the effectiveness of pasteurization and safe storage. The final product exhibits precise physical properties: a dense yet creamy mascarpone layer with stable gel structure, a sponge layer of ladyfingers soaked to optimal moisture content, and a fine cocoa powder surface finish. The internal protein and fat matrix supports the structure while retaining a soft, spoonable texture. Each spoonful reflects careful coordination of ingredient ratios, temperature, shear forces, and layer integration. Even at a microscopic level, the structural integrity is controlled. Proteins in the mascarpone form a cohesive network, trapping air minimally. Fat droplets are distributed evenly, and moisture from coffee infusion is absorbed uniformly in the sponge layer. Cocoa particles adhere lightly to the top without penetration, ensuring visual consistency and flavor profile. A high-volume Dunkin' Donuts line is built around delivering dough or batter to hot oil in the same condition every minute, because frying fixes shape, crumb, and surface in seconds and leaves little opportunity to correct variation downstream. Ingredient conditioning starts the process. Flour is sieved to remove lumps and aerated for consistent hydration. Sugar is screened so crystal size stays stable and dissolves predictably in mixers. Salt and leavening are pre-blended, so distribution is uniform at low inclusion rates. Fats are tempered so their plasticity is consistent for dough systems, or melted and cooled to a target temperature for batter systems. Eggs and dairy liquids are tempered because small temperature shifts change emulsion behavior and batter viscosity. Water temperature is selected to land the final dough or batter in a narrow temperature window. For yeast-raised donuts, the front end is a developed dough that must proof consistently. Flour enters a mixer and is hydrated with water and dairy liquids, while yeast is dispersed early, so fermentation is uniform. Mixing begins slowly to hydrate without dusting, then increases speed to develop gluten. Gluten development is tuned to a target elasticity that can trap gas but still sheet cleanly. Fat is added after initial gluten formation, so it softens the network without blocking development. Eggs and emulsifiers are incorporated in a controlled sequence, so they form a stable dispersion inside the dough rather than separating into streaks. Dough temperature is managed as a primary control variable. Mixing friction generates heat, so water temperature and mix time are adjusted to reach a target dough exit temperature. That exit temperature controls dough stiffness and yeast activity. The dough then enters a timed rest, where moisture equalizes and gluten relaxes. Relaxation reduces snapback in sheeting and improves cut accuracy, while early fermentation begins creating fine gas cells without fully expanding the dough. The rested dough feeds a divider and sheeter. Dividing stabilizes feed rate into rollers, so thickness remains steady across time. Sheeting reduces thickness through several roller gaps rather than one large reduction to avoid stress lines that later become weak points in the fryer. Gauge rollers lock the final sheet thickness, which becomes a main determinant of donut weight and final crumb thickness. Rotary cutters punch rings at line speed, cutting an outer diameter and removing the center plug. Cutter sharpness matters because dull edges compress the dough and create ragged rims that absorb more oil and brown unevenly. Scrap around the cutouts is lifted and returned to the dough stream at controlled ratios, because high scrap ratios increase working and shift gluten development. Cut rings move into proofing, where the dough expands to near final volume. Proofing is run at controlled temperature and humidity. Temperature sets yeast gas production rate, and humidity prevents a dry skin that would restrict expansion and cause blowouts. Proof time is tuned to reach a target volume and cell structure. Underproof yields dense donuts with limited lift. Overproof yields fragile donuts that collapse when moved or flipped in oil. For cake-style donuts, the line works with a chemically leavened batter rather than a fermented dough, so the objective is minimal gluten with uniform leavening dispersion. Dry ingredients are pre-blended, so chemical leavening and salt are evenly distributed. Liquid ingredients are blended separately, so eggs and fats emulsify before meeting flour. The streams combine and mix only long enough to hydrate flour and remove lumps, because overmixing develops gluten and produces tough donuts with irregular cracking. Batter temperature is held tightly because viscosity must remain stable for depositing. If batter is too thin, it spreads and loses ring definition when it hits oil. If too thick, it deposits unevenly and can trap air pockets that create voids. Depositing forms rings directly into the fryer for cake products. A depositor meters batter through shaped nozzles with timing synchronized to the fryer conveyor, so spacing is consistent. Deposit weight is controlled by pump stroke or timed flow. The batter must release cleanly from the nozzle and hold its shape long enough for the surface to set in oil. Frying is the setting step for both routes. Oil temperature, dwell time, and turnover are the controlling variables. When a donut enters oil, surface water flashes to steam, creating outward pressure that expands the structure and delays oil penetration during the earliest phase. Starch gelatinizes at the surface and forms a crust. Proteins coagulate and lock the structure. Browning reactions accelerate as the surface dries, creating the final color and flavor profile of the crust. Yeast-raised rings usually float and fry on one side first. Conveyor speed determines how long the first side sets before a turning mechanism flips the donut. Flip timing is critical. Flipping too early deforms the ring and creates flat spots. Flipping too late creates an overly thick crust on one side and uneven color. The second side fry completes structure set and balances moisture loss so the donut does not warp. Cake donuts set more quickly because the batter begins as a suspension with chemical gas release and rapid heat penetration. Fry conditions are tuned so the surface sets at the right moment. If the surface sets too fast, expanding gases crack the crust and create blowouts. If the surface sets too slowly, the batter spreads and forms misshapes. Residence time and temperature are adjusted together to manage this balance. Oil management runs continuously because crumb fragments and batter fines burn and darken the oil, changing heat, transfer, and color development. Filtration removes fines and keeps the oil clean. Oil is circulated to maintain uniform temperature across the fryer width and prevent striping. Controlled oil turnover keeps frying behavior stable, so the same dwell time produces the same color and oil pickup. As donuts exit the fryer, surface oil is removed immediately. Drain belts and vibrating conveyors shake off free oil, and air blowers strip oil from creases. This step is important because surface oil interferes with glaze adhesion and increases greasy feel. The donuts then enter cooling, where internal steam condenses, fats begin to crystallize, and the crumb firms. Cooling is staged to stabilize structure and prepare for finishing. Hot donuts are soft because fats are liquid and the crust is still plastic. As they cool, the crust becomes rigid and the interior moisture redistributes. Cooling airflow is controlled so the surface does not dry too fast, which would create a tough crust that flakes under glaze. Cooling also prevents packing too warm, because warm donuts release moisture into packages and soften coatings. Glazing and icing are applied in controlled viscosity windows. A classic sugar glaze is mixed to a defined solids level and held warm enough to flow as a thin film. Donuts pass under a glaze curtain or are dipped, and the excess drains as they travel on a setting conveyor. As water evaporates, the glaze crystallizes into a smooth shell. Chocolate or fat-based icings are heated to a target flow temperature and applied by curtain or dipping, then set by cooling so the fat network solidifies without cracking. Powdered sugar or cinnamon sugar finishes are applied while the donut surface still has slight warmth and tack. The donuts pass through a shower or drum that distributes powder evenly, and screens recover excess. Toppings are applied during the short tack window before coating set. Feeder's meter sprinkles or nut pieces at a rate synchronized to belt speed, so coverage stays uniform without clumps. Filled donuts at an injection step after cooling reaches a firm but pliable state. Fillings are prepared to a pumpable viscosity that holds shape without leaking. Multi-needle injectors penetrate at controlled depth, and piston strokes deliver consistent doses. Needle retraction timing is coordinated to reduce backflow and surface smearing. If a side fill format is used, a controlled slit is cut, and a nozzle deposits filling into the pocket. Then the product passes through a brief set zone, so the filling surface stabilizes. Packaging is designed around protecting finishes and managing moisture exchange. Donuts intended to stay soft use barrier materials that reduce moisture loss. Donuts with a crisp shell need packs that prevent moisture gain that would soften crust and glaze. Cartons and clamshells protect toppings from abrasion and reduce contact marks, while flow wrap provides strong moisture control but requires the surface to be fully set to avoid smearing. Seal temperature and dwell are tuned so seals close without heating the donut enough to soften coatings. A Chick-fil-A style breaded chicken fillet is produced by turning trimmed poultry breast into uniform portions, conditioning the meat so it stays juicy after cooking, applying a controlled flour and batter system that bonds tightly, setting the coating quickly in hot oil, then chilling and packaging so every fillet reheats with the same crust and bite. Production starts with raw poultry arriving chilled and moving into size reduction and standardization. Breast meat is trimmed to remove thin tails and ragged edges that would overcook and create hard spots. The trimmed pieces are sorted by weight band so the forming line can hold a tight portion range. Consistent portion mass is a core control because fry time and internal temperature rise rate depend on thickness. The meat is then conditioned to stabilize moisture, retention, and texture. A measured solution is prepared from water, salt, and functional ingredients that improve binding and reduce purge. This solution is mixed to a defined concentration and held cold so it does not warm the meat. The solution is introduced to the meat by tumbling or by injection followed by tumbling. Tumbling cycles alternate between rotation and rest so the solution distributes through muscle fibers without tearing them. Vacuum tumbling is often used because removing trapped air improves uptake consistency and reduces voids that can appear as soft pockets after cooking. The endpoint is judged by pickup percentage and by uniform surface tack rather than by extended mixing time. Once conditioned, the meat is portioned into fillet shapes. If whole muscle fillets are used, they are pressed to a consistent thickness using calibrated rollers. Pressing is gentle and aims to widen and even the piece without shredding. Thickness control matters because a thick center can remain undercooked when the crust looks done. If formed fillets are used, the meat is ground coarsely and then shaped in a forming machine. But a classic sandwich fillet format typically relies on whole muscle thickness control rather than full comminution. After shaping, the fillets pass through a brief chill stage. Chilling firms the surface proteins and improves handling so the pieces do not smear when they enter the coating system. Chilling also stabilizes the pickup behavior of the next layers because warmer surfaces thin the batter and increase coating variability. The coating system is built as a multi-step adhesion stack. The first layer is a pre-dust, usually a seasoned flour blend that absorbs surface moisture and creates a dry interface. Pre-dust is delivered as a curtain or bed where fillets tumble and roll so all surfaces are covered. Excess pre-dust is removed by gentle shaking because too much dry flour creates thick patches that later detach. After pre-dust, the fillets enter a batter stage. The batter is mixed in tanks that maintain solid suspension and viscosity. Viscosity is monitored because it determines coating thickness and how the batter bridges surface contours. Batter temperature is controlled because warm batter flows too thin and produces weak coating, while cold batter thickens and creates ridges. The fillets pass through a batter waterfall or immersion where every surface is wetted. Air knives can remove excess and set a uniform film thickness. Breading follows immediately while the batter is still wet. Breading is usually a seasoned flour system with a defined particle size distribution. Some formats use a mix of fine flour and larger crumb to create a textured crust. The fillets travel through a bed of breading while top belts press lightly to embed particles. This compression step is critical because it turns loose surface flour into a mechanically locked layer that will survive frying and later handling. Excess breading is removed so the crust is thick but not clumpy. If the target crust requires a distinctive craggy surface, the line can use a second batter and breading pass. The first pass builds the base, and the second pass builds height and texture. Each pass is tuned, so the coating does not become so heavy that it insulates the meat and slows cooking. After breading, the fillets enter a short setting zone before frying. This can be a brief rest on a belt that allows the batter to hydrate the dry breading and form a cohesive paste at the interface. Hydration improves adhesion and reduces blow-off in the fryer. The rest time is short because the coating must not become wet enough to smear. Frying is the structure-setting step. Fillets enter a continuous fryer where oil temperature and dwell time are tightly controlled. The fillets are held under oil by a top belt so they cook evenly and do not float and curl. As the fillet enters oil, surface water flashes to steam. That steam creates outward pressure that expands the coating slightly and forms pores. Starches in the batter gelatinize and then begin to dry into a rigid network. Proteins in the batter coagulate and lock the crust shape. Oil temperature is chosen to set the crust quickly while allowing heat to penetrate the meat at a controlled rate. If oil is too hot, the crust darkens before the center reaches the target internal temperature. If oil is too cool, the crust sets slowly, absorbs more oil, and becomes heavy. Dwell time is set by belt speed and fryer length. Bed loading is controlled because overcrowding reduces oil circulation and causes uneven color. Oil management runs continuously because breading fragments break off and will burn if not removed. Filtration systems remove fines and keep the oil clean. Circulation keeps temperature uniform across the fryer width. Fresh oil makeup maintains quality so heat transfer and browning stay consistent. At fryer exit, surface oil is removed by vibration and air stripping. Removing surface oil reduces greasiness and improves how the fillets package and reheat. The fillets then enter a cooling stage. Cooling stabilizes the crust and lets internal steam pressure fall gradually. If cooling is too fast, the crust can contract and separate slightly. If cooling is too slow, residual heat can soften the coating and reduce crispness. From here, the process can diverge depending on distribution format. For a chilled product, the fillets are cooled rapidly to a target core temperature and held under controlled conditions. For a frozen product, the fillets enter an individual quick freezer. The freezer uses high-velocity cold air to freeze quickly and preserve crust porosity. Rapid freezing forms smaller ice crystals and reduces moisture migration that would soften the crust later. The pieces are spaced so they freeze individually and do not stick. After freezing, the fillets are screened and inspected. Broken coating fragments are removed because they increase crumbs in the package and can burn during reheating. Size and weight checks confirm portion control. Optical systems can reject misshapes and incomplete coating. Metal detection can be placed after freezing when product flow is stable. Packaging begins with portioning. Multi-head weighers or counting systems assemble target weights for bags or cases. Drop heights are minimized because frozen breading can chip and create fines. Bags are formed from barrier film that limits moisture exchange. Moisture control is crucial because the crust will lose crisp potential if it picks up moisture in storage. Seals are made with controlled heat so the film closes without wrinkles. Seal areas must remain clean because crumbs can interfere with seal integrity. For food service formats, the fillets are packed into lined cases with internal bags. Case fill patterns are chosen to reduce compression on lower layers. Cases are sealed and coated. Pallet stacking is designed to avoid crushing that would fracture crust. Storage temperature stability prevents freeze-thaw cycles that create ice crystals on the crust and degrade reheating performance. The final product performance is engineered into the factory steps. Meat conditioning sets moisture retention, so the fillet stays juicy after a high heat finish. Pre-dust and batter create a bonded interface, so the crust does not slide off when bitten. Breading particle size and compression set the surface texture. Fry temperature sets pore structure and crust rigidity. Cooling and freezing preserve that structure. Packaging maintains low moisture exchange, so the crust can crisp again during final cooking or reheating. A McDonald's-style hamburger is manufactured by turning beef trim into uniform patties that cook the same way every time, producing buns that stay soft yet resilient after freezing and toasting, then portioning and packaging each component so it can be assembled rapidly with consistent texture. Beef patty production starts with raw trim selection and temperature control because fat level and grind behavior determine bite and shrink. Beef arrives as chilled trim in defined lean to fat bands. The trim is inspected for hard connective pieces that would create tough spots and for excessive surface fat that would smear during grinding. Trim is kept cold from the start because warm fat smears into a paste, which causes dense patties and poor cook texture. The trim enters a coarse grinding stage first. Coarse grinding breaks the meat into uniform chunks without turning it into an emulsion. This is done through a grinder plate with larger holes, so particle definition is preserved. The coarse ground meat then moves to blending, where multiple trim lots are combined to hit a target fat percentage. Blending uses paddles that fold the meat rather than whip it, because air incorporation and overworking change density and can create voids. After blending, the meat is ground again through a finer plate to create the target particle size distribution. Particle size affects how the patty binds and how it releases juices. Too coarse yields a crumbly patty that breaks at the edges. Too fine yields a tight, rubbery bite. Grind temperature is monitored continuously because friction can warm the meat. If temperature rises, the line slows or adds colder meat to keep the mix in range. The blended grind is moved quickly to forming. Forming turns the loose ground meat into patties with a fixed diameter, thickness, and mass. A patty former meters meat into a cavity and compresses it to a set density. Compression must be strong enough to make the patty hold together during freezing and handling. Compression must not be so strong that the patty becomes dense and loses its characteristic bite. Formers often imprint a pattern on the surface. The imprint increases surface area and helps heat penetrate evenly during cooking. Weight control is enforced at the forming head. Portioning is measured by volume with density control or by mass flow with feedback. Tight weight control is important because cook time is fixed in high volume systems, so patties must reach target internal temperature within the same dwell. Patty thickness control is equally critical because a thicker patty heats slower and will be underdone when a thinner one is correct. Immediately after forming, patties enter a rapid freezing step. Freezing locks the shape and prevents patties from sticking together. Individual quick freezing is used with high-velocity cold air. The patties travel on a belt through a tunnel where cold air freezes the surface quickly first, then drives the core down to the target temperature. Rapid freezing forms smaller ice crystals and preserves texture better than slow freezing, which can create larger crystals that damage muscle structure. Patties are then separated, counted, and stacked into interleaved layers. Interleaving uses paper or film sheets between patties to prevent adhesion and simplify later separation. Stacking pressure is controlled so patties do not deform. The stacks are bagged or boxed in a way that limits moisture exchange and protects edges from chipping. Metal detection and weight verification typically occur after freezing when product flow is stable and consistent. The bun is produced on a separate bakery line, built around controlling softness, resilience, and freeze-thaw stability. Flour is sieved and blended to a target protein range because gluten strength controls how the bun holds up to toasting and compression. Sugar and salt are metered precisely. Yeast is staged as a controlled addition because fermentation rate must match line speed. Fats and emulsifiers are included to soften crumb and extend softness after freezing. Water temperature is controlled because dough temperature drives fermentation speed and dough handling. Mixing develops gluten to a defined endpoint. The dough must be strong enough to trap gas and rise, but not so strong that the bun becomes chewy or tough. Mixing begins with hydration and then transitions into higher energy kneading until the dough reaches a smooth, elastic state. Dough temperature is checked at discharge because mixer friction can warm the dough and accelerate fermentation. If dough exits too warm, proof times shorten and the process becomes unstable. After mixing, dough is rested and then divided. Dividers. Portion dough into equal pieces by weight. Portion weight directly determines bun diameter and height. Divided pieces are rounded to create surface tension, which supports a uniform shape during proofing. Rounded dough balls then rest briefly to relax so they can be shaped without tearing. Shaping forms the final bun geometry. Dough balls are flattened slightly and placed onto baking trays or oven bands. Proofing follows in a warm, humid environment. Proof temperature controls yeast activity and gas generation. Humidity prevents skin formation so the bun can expand smoothly. Proof time is tuned so buns reach a target volume and internal cell structure. Underproof yields dense buns with low softness. Overproof yields weak buns that collapse and wrinkle. Baking sets structure and dries the bun to a controlled moisture endpoint. Tunnel ovens run zoned heat so the surface sets and the crumb cooks without excessive crust hardness. Early oven zones drive oven spring as trapped gas expands. Mid zones gelatinize starch and coagulate proteins to fix the crumb. Later zones develop a light crust color and finish internal moisture reduction. The bun must not be too dry because it will feel stale. It must not be too wet because it will collapse and compress poorly. After baking, buns cool on conveyors with controlled airflow. Cooling sets the crumb as fats crystallize and moisture redistributes. Slicing is done after cooling reaches the right firmness. Slicers cut buns horizontally with blades that maintain a consistent hinge or full separation depending on format. Slice depth is controlled because it affects later toasting behavior and bun strength during assembly. Sesame seeding, if used, is applied either before baking for adhesion or after with an adhesive wash depending on equipment design. For high volume distribution, buns are often frozen. Freezing protects softness and allows stable inventory. Buns enter a freezing tunnel where surface is frozen quickly to maintain shape. Packaging then seals buns in bags with barrier properties that limit dehydration. Bag seals must be strong because freezer burn dries bun surfaces and changes toasting behavior. Cheese slices, pickles, onions, and sauces are produced as separate streams with their own controls. But in the context of assembly readiness, the main requirement is portion uniformity and stable handling. Cheese is portioned into slices with tight thickness. Pickles are cut to consistent thickness, so acidity and crunch are predictable per unit. Dehydrated onions are produced by slicing onions and drying them to a low moisture level, then sizing flakes, so rehydration in the final product is consistent. Sauces are mixed as emulsions with defined viscosity, so dispensing systems deliver repeatable weights. Packaging and logistics are treated as part of the production system because the end product depends on thaw and cook behavior. Frozen patties are boxed in counts that match downstream loading systems. Boxes are designed to stack without crushing product. Buns are packaged to reduce moisture loss and protect shape. Temperature stability through storage is critical because freeze-thaw cycles create ice crystals that damage texture and cause condensation inside packs. The final operational transformation happens at the cooking line, where frozen patties are separated and cooked on a clamshell grill. The clamshell grill is engineered for repeatability. Patties are loaded onto a lower hot platen, and then a top platen closes to contact both sides. Contact cooking on both sides reduces cook time and ensures uniform heat penetration. Time and platen temperature are fixed, which is why patty thickness and mass upstream must be consistent. The surface imprint on the patty increases contact and helps fat render evenly. A PET preform enters the Pepsi line as a short, thick tube of transparent plastic. Its bottleneck is already finished. The threads, sealing surface, and tamper ring support are molded into place before the body is expanded. The lower section is still compact and heavy, holding enough plastic to form a full bottle. The preforms drop into a feeder, where mechanical tracks orient them neck up. They travel into a heating oven in single file. Infrared lamps warm the body of each preform, while rotating holders spin it continuously. Rotation spreads heat evenly around the plastic wall. The neck remains cooler because its dimensions must not change. When the plastic reaches the correct softness, transfer arms lift each preform into a blow molding station. A steel mold closes around it. Inside the mold is the final Pepsi bottle shape, including the shoulders, label panel, grip features, and pressure-resistant base. A stretch rod drives downward through the heated preform. It pulls the softened plastic lengthwise. Almost immediately, compressed air fires into the interior. The plastic balloons outward until it touches every chilled surface of the mold. The small tube becomes a full bottle in a fraction of a second. The mold opens. A clear, lightweight bottle leaves the station by its neck ring. It is still warm, but already rigid enough for conveying. The bottle moves through overhead air conveyors, suspended below rails, while streams of air push it forward. Before filling, the empty bottles enter a rinser. Each bottle is gripped by the neck, flipped upside down, and exposed to filtered rinsing air or treated water. Any loose particle is removed from the inside surface. The bottle drains briefly, turns upright again, and enters the filling section. While the packaging line forms and cleans the bottles, the beverage is assembled inside closed stainless steel equipment. Water enters the plant treatment system first. It passes through particle filters that remove suspended solids. Activated carbon stages remove unwanted tastes and odors. Additional filtration and conditioning equipment brings the water to a stable mineral and clarity specification. The treated water collects in sealed storage tanks. Level sensors monitor the volume. Temperature probes track the condition of the water. Pumps send part of it towards syrup production and keep another controlled stream available for final beverage blending. Pepsi syrup begins in a mixing tank with a measured charge of treated water. The tank agitator starts turning, creating a deep circular flow. Sweetener is introduced into this moving liquid. Depending on the production formula, the sweetener may be dry sugar, liquid sugar, or a liquid sweetening system. When granulated sugar is used, the crystals disappear into the rotating water. The liquid gradually becomes denser and more reflective. Mild heat can assist dissolution, allowing the sweetener to blend fully without leaving gritty material behind. The sweetened liquid leaves the dissolving tank through a filtration stage. Fine filters catch undissolved particles before the syrup reaches later machines. The filtered stream moves into a finished syrup vessel. Pepsi concentrate is metered into this tank through enclosed pipework. It enters as a dark, highly concentrated stream. Pumps and flow meters control the quantity precisely. As the agitator turns, the concentrate folds through the sweet base, rapidly changing its color and aroma. The concentrate supplies the specific cola flavor system and caramel-toned appearance required for Pepsi. Acidity ingredients are incorporated according to the formula. Each addition is measured before it enters the tank, and mixing continues until the syrup reaches a uniform condition throughout the vessel. The finished syrup is too concentrated to fill directly. It flows to a proportioning unit, where it will meet a much larger stream of treated water. The proportioner receives syrup through one controlled line and water through another. Flow meters measure both streams continuously. Automatic valves adjust their movement so the mixing ratio does not drift. The system corrects itself immediately when flow or pressure changes. Inside the blending chamber, dark syrup spreads into the water. The beverage reaches its final sweetness, flavor concentration, acidity, and color, but it still lacks carbonation. At this moment, it is flat Pepsi. The blended liquid enters a chilling system. It passes through thin channels inside a heat exchanger while a cold cooling medium flows nearby on the opposite side of metal plates. Heat leaves the drink quickly. The temperature drops without exposing the beverage to outside air. Chilling prepares the liquid for carbon dioxide. Cold Pepsi can absorb gas more efficiently and can be filled with less foaming. The beverage may also move through a deaeration unit, where reduced pressure draws unwanted dissolved air from the liquid. Small bubbles rise out of the stream before it continues. Carbon dioxide enters through pressure regulators and filtered gas lines. In the carbonator, the chilled beverage is held under controlled pressure while carbon dioxide dissolves into it. The liquid becomes lively and sparkling without forming uncontrolled foam inside the system. From this point onward, the beverage must remain under pressure. Closed pipes carry carbonated Pepsi directly toward the filler bowl. The rotary filling machine is surrounded by continuously moving empty bottles arriving from the rinser. A star wheel separates the bottles into exact intervals and guides each one under a filling valve. The bottle lifts into sealing contact with the valve. Gas pressure inside the bottle is balanced with the pressure in the filler before liquid enters. This prevents the carbonated drink from surging or erupting into foam. The valve opens. Cold Pepsi flows smoothly down the inside wall of the bottle. The liquid level rises in a controlled column, dark and glossy, beneath the overhead machine lights. When the exact fill point is reached, the valve closes. Each filled bottle moves away from the filler and immediately toward the capper. There is little open travel between these stages because the carbonation must be captured quickly. Plastic caps arrive in bulk and enter a sorting unit. The feeder turns every cap into the same orientation and sends them down a chute. Rotating capping heads collect the caps one by one. A filled bottle passes underneath. The capping head lowers, places the cap over the threaded neck, and turns it with a measured torque. The liner presses against the sealing surface. The tamper band locks below the bottle ring. The beverage is now sealed inside a pressure-tight container. Other Pepsi package lines use different sealing equipment. Empty aluminum cans pass through air rinsers before filling, then receive metal lids. In the seamer, each lid and can edge are folded together by rotating rolls. The double seam traps the carbonation inside the can. Glass bottles can receive metal crown caps pressed and crimped around the bottle mouth. After sealing, the bottles travel through inspection systems. Sensors check the liquid level through the bottle wall. Cameras verify that every cap is present, straight, and fully seated. Other detectors examine bottle shape, cap position, and possible leakage. A bottle outside tolerance is removed from the conveyor by a rapid pusher or directed air burst. The correctly filled stream continues without pausing. The bottles now enter the labeling area. Printed plastic label film unwinds from a large roll. Registration sensors read tiny marks in the printed pattern so each label is cut at exactly the correct point. The labeler cuts individual pieces of film and transfers them towards spinning bottles. A small amount of adhesive fixes the leading edge to the bottle surface. As the bottle rotates, the label wraps around its body. A second adhesive point secures the trailing edge. Rollers and brushes smooth the film against the bottle panel. The label sits tightly around the container, displaying its blue, red, and white print while leaving the cap and liquid visible above and below it. Some package formats use pressure-sensitive labels instead. These are peeled from a backing liner and pressed onto the container by soft rollers. For cans, the printed design is normally already applied to the metal body before beverage filling. Every finished container receives production coating. An inkjet head sprays tiny droplets onto the cap, bottle shoulder, label area, or can base as the package moves past. The coat is applied in milliseconds, leaving a readable batch and time mark. Because the beverage has been chilled, moisture may gather on the outside of the package. The containers pass through an air knife station. Narrow blades of fast-moving airstrip droplets from the cap, bottle shoulder, label seam, and base. The surface becomes dry before secondary packaging begins. Guide rails then divide the bottle flow into several lanes. Timing screws adjust the spacing. Collating equipment gathers bottles into predetermined pack patterns. A continuous stream of single bottles becomes groups arranged in rows. For shrink-wrapped formats, a film sheet surrounds each group. The pack enters a heat tunnel. Hot air causes the film to contract around the bottles, tightening against the shoulders and lower walls. The individual containers become one handled unit. A dark stream of Dr. Pepper concentrate enters a moving tank of sweet syrup and disappears beneath the turning surface. The tank is sealed stainless steel with an agitator rotating from below. Inside, the syrup is already dense and smooth. It has been prepared from treated water and a measured sweetener system, blended until no dry crystals or heavy streaks remain. When the concentrate enters, the liquid changes quickly. Its color deepens to a rich brown, and the entire batch takes on the concentrated flavor base that will later become finished Dr. Pepper. The concentrate is not the final drink. It is a powerful flavor system measured in small quantities against a much larger volume of water and sweetener. Metering pumps deliver it through closed piping. Flow meters or weighed vessels confirm the addition. The agitator keeps pulling liquid inward, folding the concentrate through the syrup until the mixture reaches the same strength and color from top to bottom. Before this stage, water has already moved through its own preparation system. Incoming water passes through particle filters that remove suspended material. Activated carbon beds reduce unwanted tastes and odors. Additional polishing equipment brings the water to a stable mineral condition and clarity. The finished water collects in enclosed storage tanks, ready for syrup production and final dilution. Sweet syrup forms in a separate tank. A programmed amount of treated water enters first. Sugar or another specified sweetener is added, while large mixer blades rotate. Dry crystals, when used, sink into the moving liquid and dissolve as heat and agitation work through the batch. The mixture becomes thicker, clearer, and more reflective than plain water. The syrup then passes through fine filtration. Any undissolved material is removed before it can reach valves, pumps, or filling heads. From there, the filtered sweet base receives the Dr. Pepper concentrate and required formula additions. The finished syrup is intense, heavy, and still. It contains the beverage character, but it is far too concentrated and has no carbonation. The syrup leaves its holding tank through sanitary pipework and reaches a proportioning unit. Another pipe brings treated water from storage. The two streams remain separate until their flow rates are measured. The proportioner checks them continuously, opening and closing automatic valves in tiny movements to maintain the required blend ratio. Inside the blending chamber, the concentrated syrup is diluted. The thick, dark liquid thins immediately as it merges with water. Its viscosity drops, but its color remains deep. The mixture now has the sweetness, acidity, and flavor strength of Dr. Pepper, although it is still flat and warm compared with the finished drink. The flat beverage moves into a chilling section. It passes through narrow passages in a plate heat exchanger. On the opposite side of each thin metal plate, chilled fluid draws heat away. The drink temperature falls rapidly without exposing the liquid to open air. Cooling matters because carbon dioxide dissolves more readily into a cold beverage. A chilled drink also behaves more cleanly inside the filler, with less foam breaking out when it enters the package. The colder stream continues toward the gas handling equipment. Before carbonation, dissolved air may be removed from the water or blended beverage. In a deaeration vessel, reduced pressure encourages trapped gases to escape. Tiny bubbles rise out of the liquid as it flows through the chamber. The treated stream leaves with less unwanted gas competing with the carbon dioxide that will be added next. Carbon dioxide arrives through regulated stainless steel lines. Pressure control equipment stabilizes the gas before it enters the carbonator. Inside that enclosed machine, cold Dr. Pepper and carbon dioxide meet under pressure. The gas dissolves into the liquid, building the sharp, sparkling texture of the finished beverage. The carbonated drink stays inside pressurized piping from this point forward. It cannot be allowed to lose gas before sealing. Pumps and valves carry it toward the filler, while container lines approach from different directions. On a can line, empty aluminum cans begin as open cylinders arriving in closely packed rows. Guide rails narrow the flow into controlled lanes. The cans enter a twist rinser where curved tracks turn each container upside down. Filtered air or rinsing fluid blasts the interior. The cans drain, rotate upright, and move directly toward filling. A bottle line starts differently. PET preforms arrive as small plastic tubes with fully molded neck threads. Feeders orient the preforms and place them onto carriers. They enter an infrared oven, rotating as heating lamps soften the body evenly while leaving the neck stable. The hot preforms transfer into bottle molds. Each mold closes with the exact shape of the final container formed into its inner surface. A stretch rod extends the soft plastic downward. Compressed air then expands it outward against the chilled mold wall. In an instant, the thick preform becomes a full-size bottle with shoulders, side panels, and a pressure-resistant base. Fresh bottles leave the mold held by their neck rings. Air conveyors move them toward rinsing. Each bottle is inverted, cleaned internally with filtered air or treated water, drained briefly, then returned upright. The bottles are now empty, clear, aligned, and ready to capture carbonated Dr. Pepper. The filler is a large rotating machine. A circular bowl holds pressurized beverage above many filling valves. Containers enter through a star wheel that spaces each one precisely. Every can or bottle is delivered under its own valve as the carousel continues turning. For bottles, the neck presses into sealing contact with the filling valve. For cans, the open top is positioned beneath the filling assembly. The container is prepared for the pressurized liquid, so gas does not erupt violently when the drink enters. Pressure equalization keeps the beverage calm. The valve opens. Dr. Pepper flows into the container in a controlled path, often directed along the inner wall to limit turbulence. In transparent bottles, the dark liquid rises smoothly from the base. A thin layer of bubbles appears near the top, then settles as the correct fill level is reached. The valve closes at the programmed point. Correct headspace remains above the liquid, allowing the sealed package to contain internal pressure properly. The filled container moves immediately out of the filler toward its closing machine. Cans receive lids first. A lid feeder separates thin aluminum ends and positions one over each filled can. The can then enters a seamer. Rotating tooling folds the lid curl and can flange together. One set of rolls forms the hook. Another compresses it into a tight double seam. The can leaves with the carbonated beverage trapped beneath a narrow metal seal. Peter bottles travel beneath rotating capping heads. Plastic caps arrive through a sorting feeder, all facing the same direction. A head picks up one cap, lowers it onto the bottleneck, and turns it to a controlled torque. The tamper band passes over the neck ring and locks into place as the closure tightens. Glass bottle formats use crown caps. A crown is positioned on the bottle mouth and pressed downward. The capper crimps its ridged skirt beneath the glass finish. The sealed glass bottle continues with the same pressurized drink enclosed inside. Sealed packages enter inspection immediately. Fill level sensors examine the amount of liquid. Cameras inspect cap position, crown placement, can lid presence, bottle shape, and package condition. Seam monitoring systems can evaluate can closure quality. Any package outside the programmed limits is removed from the line by a fast reject mechanism. Bottles then require labeling. A roll of printed label film unwinds beside the moving conveyor. Registration sensors read marks on the web, so each label is cut in the correct position. The cut label reaches a rotating bottle, receives small adhesive contact points, and wraps smoothly around the body. Rollers press the label against the bottle surface. The film tightens across the label panel without folds or loose edges. Glass packages may instead receive glued paper labels or pressure-sensitive labels applied by transfer pads and smoothing brushes. Cans usually arrive with their exterior design already printed, so they bypass wraparound labeling. Bottles and cans both pass the coding station. Inkjet heads fire tiny droplets onto a cap, bottle shoulder, label surface, or can base. Each package receives a compact production mark while remaining in motion. Because filling uses chilled liquid, condensation can form on the outside of the containers. The sealed packages move through air knives. Narrow, powerful sheets of air push droplets away from cap rims, shoulders, label seams, can lids, and bases. Dry packages travel more reliably through the equipment that gathers them into larger units. An empty aluminum can drops into a twisting rail and turns upside down before a single drop of Red Bull enters it. The can is already formed, printed, and open at the top. Its walls are thin, lightweight, and shaped to withstand internal pressure once the carbonated drink is sealed inside. As the can moves through the rinser, filtered air blasts its interior. The can rotates upright again and joins a tightly spaced stream heading toward the filler. At the same time, the beverage is being assembled inside closed stainless steel tanks and pipework. The liquid begins with treated water. Incoming water passes through filtration equipment that removes fine suspended particles. Activated carbon treatment removes unwanted tastes and odors. Additional polishing stages stabilize clarity and mineral behavior. The treated water is collected in sealed holding tanks fitted with level probes, temperature sensors, and controlled outlet pumps. A portion of this water moves toward the syrup preparation area. Red Bull is built differently from a dark cola. The finished liquid is pale and translucent, so the dissolved ingredients must create a clear, uniform beverage without visible sediment or cloudiness. A measured amount of treated water enters a blending vessel. The agitator begins turning beneath the surface. Sugar is introduced through a dosing system. When granulated sugar is used, the crystals fall into the moving water and begin dissolving immediately. The liquid grows heavier and more glossy as the sweetener concentration rises. Temperature control assists this stage. Warm liquid dissolves crystalline ingredients more efficiently, but the heat is regulated so later ingredients can be added under stable conditions. The vessel does not boil the mixture. It builds a clean, pumpable base that can carry the beverage components evenly. Once the sugar solution is smooth, it passes through filtration. Fine filters catch any remaining undissolved material before the liquid reaches precision dosing equipment. The filtered base returns to a blending tank or flows into an inline mixing system. Acidity components are added next. They enter as measured liquid or dissolved ingredient streams. The agitator folds them through the sweetened water. The base changes chemically, developing the sharp structure needed beneath the sweetness and carbonation. Energy drink ingredients are introduced in controlled quantities. Caffeine, taurine, vitamin ingredients, and flavor components are weighed or metered before entering the blend. Some arrive as prepared solutions, so they disperse quickly. Others are dissolved in a separate small tank before being pumped into the main stream. The dosing stage requires careful mixing because each ingredient must spread evenly through a large liquid volume. A concentrated addition entering one point in the tank cannot remain there. The agitator draws the stream downward, pushes it outward, and circulates it through the vessel until the blend has consistent concentration throughout. Flavor ingredients join through closed lines. They are added in small, precisely controlled amounts because they influence the final aroma and taste far more strongly than their volume suggests. The mixture remains light in color, unlike the deep syrup formed during cola production. The prepared beverage base is still stronger than the final drink if it has been assembled as a concentrate. It flows toward a proportioning unit, where another treated water stream meets it. Flow meters monitor both liquids. Automatic valves make continuous adjustments, so the formula remains steady as production runs at high speed. As the two streams combine, the beverage reaches its final dissolved ingredient concentration. It is now sweetened, acidified, flavored, and evenly blended, but it is not yet carbonated and is still too warm for controlled filling. The liquid passes through a heat exchanger. It flows along narrow metal channels, while chilled fluid travels through neighboring channels on the other side of thin plates. Heat leaves the beverage rapidly. The liquid remains enclosed while its temperature drops. Cold liquid absorbs carbon dioxide more effectively than warm liquid. Chilling also reduces foaming inside the filler. The canning line depends on this condition because a narrow aluminum can opening leaves little room for uncontrolled foam during high-speed filling. The chilled beverage may move through deaeration equipment before carbonation. Under reduced pressure, dissolved air is encouraged to leave the liquid. Small bubbles rise and separate from the stream. Removing excess air helps the carbonated beverage behave more predictably as it travels through the pressurized system. Carbon dioxide enters through regulated gas lines. Filters and pressure control equipment prepare the gas before it reaches the carbonator. Inside the enclosed carbonation unit, carbon dioxide contacts the chilled beverage under pressure. The gas dissolves into the liquid, producing the sparkling texture of finished Red Bull. The beverage is now kept inside sealed, pressurized piping. It flows directly toward the filling machine, where the upright, internally cleaned cans are arriving in a synchronized stream. A rotary filler receives the cans through a star wheel. The star wheel separates them into exact positions and carries them beneath individual filling valves. The filler turns continuously, with each can following a curved path beneath the pressurized beverage bowl. The filling sequence begins as the can aligns with its valve. Pressure conditions are controlled so the carbonated liquid enters without excessive agitation. The valve opens and chilled Red Bull flows downward into the aluminum container. The pale liquid rises quickly inside the can. The flow is designed to remain smooth, limiting foam and protecting the dissolved carbonation. When the correct volume is reached, the valve closes. A narrow space remains between the liquid and the top of the can, allowing the package to be sealed correctly under internal pressure. The filled can moves directly toward the lid station. Thin aluminum ends are stacked in a feeder and released one at a time. Each lid is positioned over a filled can before the open container can lose significant carbonation. The can then enters the seamer. This machine creates the pressure-tight closure without glue or heat sealing. The can body and lid rotate together while forming rolls press against their edges. The first seaming operation curls the lid edge around the can flange. The second operation compresses the folded metal tightly together. Multiple layers of aluminum interlock into a narrow double seam. The seam is compact, smooth, and strong enough to contain the carbonated drink. Sealed cans travel through immediate inspection. Sensors check the fill level without opening the package. Seam inspection systems examine the closure profile. Vision cameras look for dented cans, damaged tops, missing lids, tilted seams, or printed can defects. Any can outside the programmed tolerance is rejected from the moving line. A mechanical pusher or controlled air jet removes it, while accepted cans continue forward at constant speed. The cans then pass the coding station. A high-speed inkjet printer applies production information to the can base or another assigned surface. Tiny droplets form characters as the can moves beneath the print head. A vision reader can verify that the code is present and legible. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled, so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming, so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming, so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or Sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity, and by torque, and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing, the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. Gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the R sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further.